So here's something worth thinking about as you settle in tonight. Right now, wherever you are, there are physicists, actual working physicists, with tenure and lab coats and grant funding, who genuinely cannot agree on whether the moon exists when nobody is looking at it. I know that sounds like the kind of thing you'd hear from someone who's had too much coffee and not enough sleep, but I promise you, this is real. And it's not a fringe debate. It's not some dusty corner of philosophy that serious scientists ignore. It's the central, unresolved question sitting right at the heart of the most successful, most precisely tested, most staggeringly accurate theory that human beings have ever produced: quantum mechanics. And I want you to understand how serious this disagreement is. We're not talking about a few cranks arguing on the internet. We're talking about professors at the world's best universities, researchers at CERN and Caltech and Cambridge, people who have spent their entire careers thinking about the foundations of physics and who cannot agree on the most basic question you could ask about their theory. What does it describe? Here's what makes this so strange. Quantum mechanics works. It works better than anything we've ever built. When physicists use its equations to predict the behavior of electrons, the predictions match experimental results to 12 decimal places. 12. That's like predicting the distance from New York to Los Angeles to within the width of a single human hair. No other theory in the history of science comes close to that kind of precision. The technology in your phone, the lasers in your internet cables, the MRI machines at your local hospital, the chips in every computer on the planet, all of it is built on quantum mechanics. The theory works so well that engineers bet their careers on it every single day. And yet the people who use it, the physicists who teach it and test it and rely on it to describe reality, they cannot agree on what it actually says about the world. And I don't mean they disagree about minor details. I mean they disagree about everything. Whether particles have definite positions when nobody's measuring them. Whether the universe is one thing or an infinite number of things. Whether randomness is woven into the fabric of reality. Or whether it's an illusion created by our limited perspective. Whether the act of observation actually changes the physical world. Or whether observation is just a word we use to describe something much stranger that we haven't fully understood yet. Right now, tonight, as you lie there listening to this, there are at least 5 serious, well-developed, mathematically rigorous interpretations of quantum mechanics. Each one is consistent with every experiment ever performed. Each one makes exactly the same predictions about what will happen the next time someone runs an experiment. And each one describes a fundamentally different universe. In one of them, reality literally does not exist until someone looks at it. In another, every possible outcome of every quantum event actually happens, and the universe splits into branches, endlessly, trillions of times per second, and there are other versions of you right now, in other branches, who made different choices today, who are lying in different beds, listening to different things, or not listening at all. In a third interpretation, particles always have definite positions and follow definite paths, but they're guided by an invisible wave that reaches across all of space. In a fourth, the wave function, that mathematical object at the center of quantum mechanics, occasionally collapses all on its own, randomly, without anyone needing to observe anything. And in a fifth, quantum mechanics isn't even about the physical world at all. It's about us, about what we can reasonably expect to experience, about our beliefs, not about reality. 5 interpretations, 5 different universes. And we have no way, at least not yet, to tell which one we actually live in. Let that settle for a moment. We're not talking about speculative science fiction here. We're not talking about untested hypotheses scribbled on napkins by eccentric professors. Each of these interpretations has been developed by serious physicists, published in peer-reviewed journals, defended in heated debates at international conferences, and scrutinized by some of the sharpest minds in the world. Each one has survived every experimental test anyone has been able to devise. Each one stands today as a legitimate candidate for how the universe actually works. And they don't disagree about small things. They disagree about whether randomness is real, whether the past uniquely determines the future, whether you, right now, are the only version of yourself, or whether there are countless others living slightly different lives, in branches of reality that split off from yours a fraction of a second ago. Whether the chair you're sitting in has a definite position when nobody is looking at it, whether physics even describes an external world at all, or whether it's only, and has only ever been, about what you, personally, will experience next. These are not idle questions. These are questions about the nature of existence, and the most successful theory of the physical world that anyone has ever constructed, a theory so precise that it has never once been contradicted by experiment, cannot answer them. That's what we're going to explore tonight. Not the usual story of quantum mechanics, not the timeline of who discovered what and when, though some of that will come along naturally. What we're going to do is something different. We're going to take the strangest, most unsettling experiment in all of physics, one that every interpretation must explain, and we're going to walk through it together, slowly, carefully, and then we're going to ask, what does it mean? And we're going to discover that there isn't one answer. There are 5, and each one opens a door into a different version of reality. So here are the questions I want you to carry with you as we go. Does reality exist when nobody is watching? Is the universe truly random, or is everything determined, just hidden from view? When you make a choice, is it the only choice, or do all the other possibilities play out somewhere else? And maybe the deepest question of all, if the most successful theory in the history of science can describe what happens with breathtaking precision, but cannot tell us what is actually real, what does that say about the nature of knowledge itself? What does it mean to understand something if the understanding comes in 5 incompatible flavors? We're going to take our time with all of this. There's no rush. If some of it feels strange or hard to picture, that's fine. It felt strange and hard to picture for the greatest minds who ever lived, and some of them spent decades trying to make peace with it and never quite succeeded. If you drift off somewhere along the way, that's perfectly fine too. The ideas will still be here. And honestly, some of this might settle more comfortably in your mind when your thoughts are loose and soft, and not trying too hard to grab onto certainty. Because that's kind of the first lesson of quantum mechanics. Certainty is harder to come by than you'd think. So let's begin. And let's begin with the experiment that started all the trouble. An experiment so simple that you could set it up on a kitchen table with a flashlight and a piece of cardboard. An experiment that has been repeated thousands of times, with photons, with electrons, with atoms, even with molecules made of hundreds of atoms. And every single time, it produces a result that no one, in over a century of trying, has been able to fully explain. Not because the result is unclear. The result is perfectly clear. The problem is that the result seems to be telling us something about reality that reality has no business telling us. The experiment involves 2 slits, a source of particles, and a screen. And what happens when you run it is, without exaggeration, the reason we're having this conversation tonight. Let's start with something familiar. Imagine you're standing at the edge of a calm lake on a still morning. You pick up 2 small stones and you drop them into the water, a couple of feet apart, at exactly the same time. Each stone creates a set of ripples, spreading outward in perfect circles. And where those 2 sets of ripples meet, something interesting happens. In some places, the peak of one ripple lands right on top of the peak of the other, and you get a wave that's twice as tall. In other places, the peak of one ripple meets the trough of the other, and they cancel each other out. The water goes flat. If you were watching from above, you'd see a beautiful pattern of reinforcement and cancellation spreading across the surface of the lake. Physicists call this interference, and it's one of the most characteristic behaviors of waves. Sound waves do it, water waves do it, and light, which we've known since the early 1800s is an electromagnetic wave, does it too. Now imagine a different scenario.
You're standing in a field with a tennis ball machine. One of those devices that shoots tennis balls at regular intervals. In front of the machine, you've placed a wall with two gaps in it. Two slits, wide enough for a tennis ball to pass through. Behind the wall is a large screen covered in wet paint, so you can see where each ball lands. You turn on the machine. Some balls go through the left slit. Some go through the right slit. Some hit the wall and bounce off. And after a while, you walk around to look at the screen. What do you see? Two clusters of marks, one behind each slit. The balls that went through the left slit landed in a cluster on the left. The balls that went through the right slit landed in a cluster on the right. There's no interference pattern, no cancellation, no reinforcement, just two blobs of paint. Because tennis balls are particles. They go through one slit or the other. They don't spread out and overlap like waves. So here's the question. What happens when you do this experiment with light? In the early 1800s, a young English physician and polymath named Thomas Young set up exactly this experiment. Young was one of those figures who seems to have been good at everything. He helped decipher the Rosetta Stone. He contributed to the theory of color vision. He was fluent in at least a dozen languages. And in 1801, he carried out one of the most consequential experiments in the history of physics. He took a source of light, sunlight filtered through a small pinhole to create a coherent beam, shined it through two narrow slits cut in a piece of card, and looked at what appeared on a screen behind the slits. And what he saw was an interference pattern, bright bands where the light waves reinforced each other, dark bands where they cancelled out, a pattern that could only be produced by waves. And this was powerful evidence, really the first decisive evidence that light was a wave. Maxwell's equations, which came a few decades later, confirmed it beautifully. Light was an electromagnetic wave, oscillating electric and magnetic fields propagating through space. Case closed. Now, Young's experiment was beautiful, and it settled the question for over a century. Light was a wave. Maxwell's equations, published in the 1860s, sealed it. Light was an electromagnetic wave, a self-propagating disturbance in electric and magnetic fields, traveling at a speed that Maxwell calculated from his equations and that matched, to everyone's astonishment, the measured speed of light. By the end of the 19th century, the wave nature of light was as established as anything in physics. It bent around corners. It spread through gaps. It interfered with itself in exactly the ways that waves should. Physicists felt they understood light, and they were justified in feeling that way. But then, at the turn of the 20th century, physicists started discovering things about light that didn't fit the wave picture at all. Max Planck, a quiet, methodical, deeply conservative German physicist, was born in Kiel in 1858 into an academic family. His grandfather and great-grandfather had both been theology professors, and Planck himself had the temperament of a man who believed in order, in established institutions, in doing things the proper way.
He loved thermodynamics, the physics of heat and energy, because it felt solid, principled, built on firm foundations. He had no desire whatsoever to overthrow the established order of physics. Revolution was the furthest thing from his mind. And yet, revolution is exactly what he caused, because he was trying to solve a seemingly mundane problem. Why do hot objects glow the colors they do? When you heat a piece of iron, it glows dull red, then orange, then yellow, then white as it gets hotter. Physicists had carefully measured the exact spectrum of light emitted at every temperature, producing beautiful, precise curves. And then they had tried to explain those curves using classical physics, and the mathematics had produced a catastrophe. The equations predicted that a hot object should emit infinite energy at short wavelengths, a prediction so absurd it got the name the ultraviolet catastrophe. The experimental curves were smooth and well-behaved. The theoretical predictions blew up to infinity. Something was deeply wrong. In the year 1900, Planck found a way to fix the mathematics, but the fix required a strange assumption. He had to assume that energy wasn't emitted smoothly, continuously, the way classical physics said. Instead, energy came in discrete packets, tiny, indivisible bundles whose size depended on the frequency of the light. He called them quanta, from the Latin word for how much. Planck himself didn't really believe this was how nature actually worked. He thought it was a mathematical trick, a convenient device that happened to give the right answer. He expected someone would eventually find a proper classical explanation. He called it, in his own words, an act of desperation. He spent years trying to undo what he'd done, trying to find a way to derive the same formula without the quantum assumption. He never succeeded. And the quantum hypothesis, this reluctant mathematical patch from a conservative physicist who wanted nothing more than to preserve the established order, turned out to be the first crack in the foundation of classical physics. And then Einstein, in 1905, a 26-year-old patent clerk in Bern, Switzerland, third-class technical expert at the Swiss Federal Patent Office, a man who couldn't get an academic job and did physics in his spare time, took Planck's idea and ran with it in a direction Planck himself would never have gone. Looking at the photoelectric effect, the way light kicks electrons out of metal surfaces, Einstein proposed that light itself was made of particles, little bullets of energy, each carrying a precise amount determined by the frequency of the light. He called them light quanta. We call them photons, though that word wasn't coined until 1926 by the American chemist Gilbert Lewis. And Einstein's explanation worked with a clarity and precision that was almost startling. It explained why low-frequency light, no matter how bright, couldn't eject electrons from certain metals.
Each individual photon of low-frequency light simply didn't carry enough energy to knock an electron free. It didn't matter how many of them you threw at the surface. 1,000,000 gentle taps don't add up to one firm knock. Each photon acts alone, delivering its energy in a single interaction with a single electron. Either the photon has enough energy to liberate the electron, or it doesn't. There's no accumulation, no pooling, no gradual buildup. And high-frequency light, even very dim, could eject electrons easily, because each individual photon of high-frequency light carried more energy. A single photon of ultraviolet light packs more punch than any number of photons of red light. The energy depends on the frequency, exactly as Planck had suggested, and each photon-electron interaction is a one-on-one affair. Einstein's paper on the photoelectric effect, published in 1905 alongside his work on special relativity and Brownian motion, won him the Nobel Prize in 1921. Not for relativity, as most people assume, but for this, for showing that light comes in particles. That tells you something about how significant this discovery was considered
even in a year when relativity was already transforming physics. But the photon idea created an enormous problem, because if light was made of particles, how could it produce an interference pattern in the double-slit experiment? Particles don't interfere, they go through one slit or the other. They land in two clusters. They behave like tennis balls, not like lake ripples. And so physicists were stuck with a genuinely bizarre situation, one that would have seemed like a logical impossibility to any scientist of the 19th century. In some experiments, light behaved exactly like a wave. It produced interference patterns.
It diffracted around obstacles. It had a frequency and a wavelength, and it obeyed Maxwell's equations. In other experiments, light behaved exactly like a particle. It came in individual quanta. It delivered energy in discrete lumps. It knocked electrons out of metals one at a time, and the energy of each ejection depended not on the intensity of the light, but on its frequency. Both sets of experiments were correct. Both were repeatable. Both were precise beyond any reasonable doubt. And the two pictures, wave and particle, seemed completely, irredeemably incompatible. A wave spreads through space, occupies a region, interferes with itself. A particle is localized at a point, follows a definite path, arrives whole or not at all. How can something be both? How can it spread out like a wave when you're not looking, and then snap to a point like a particle when you are?
This was the wave-particle duality, and it was not a puzzle that could be solved by being cleverer about classical physics. It required an entirely new framework, a new set of rules, a new way of thinking about what physical reality is and how we relate to it. That new framework would arrive in the mid-1920s, in a burst of creativity that transformed physics in just a few years. And it would carry within it a mystery that, a century later, we have still not fully resolved. But the real shock, the one that still haunts physics every single day, came when experimenters developed technology sensitive enough to send photons through the double-slit experiment one at a time. This became technically feasible in the late 20th century, and when it was finally achieved, the results were exactly as strange as the theory predicted. Think about what this setup means. You're not shining a beam of light through the slits anymore. You're sending individual photons, one by one, each one a single particle of light, through the apparatus. Each photon hits the screen and leaves a tiny dot, a single point of light. After the first photon, you just see one dot. After 10 photons, you see 10 dots, scattered seemingly at random. No pattern is visible. But here's the thing. After hundreds of photons, after thousands, those randomly scattered dots start to build up into something. And the pattern they form, dot by dot, particle by particle, is an interference pattern. The same interference pattern you'd get from waves passing through two slits. Let me say that again because it really does deserve a moment to sit with. This is not a subtle statistical effect buried in noise. The pattern is unmistakable. If you look at photographs of the experiment, you can watch it build up in real time. The first 100 photons look random, dots scattered across the screen with no discernible order.
At 1,000 photons, you start to see hints of structure. Faint bands where the dots are a little denser. Gaps where they're a little sparser. At 10,000, the pattern is clear. At 100,000, it's as crisp and sharp as any interference pattern you've ever seen. Bright bands alternating with dark bands, the signature of wave interference, produced entirely by individual particles arriving one at a time, each one making its own private journey from the source to the screen. Each photon arrives at the screen as a single point. A particle. Definitely a particle. There's a detector there, and it registers a single click, a single hit at a single location. No ambiguity. And yet, when you add up the locations of thousands of individual particles, The pattern that emerges is one that can only be explained by wave interference.
As if each single photon somehow passed through both slits at the same time, interfered with itself, and then arrived at the screen as a single dot in a location that was influenced by that interference. Think about what that means for a moment. A single particle going through two openings simultaneously. A single particle somehow exploring both paths at once and producing a pattern that requires two waves to overlap and interact. And if you're lying there thinking, well, maybe the photon splits in half. Maybe half goes through one slit and half goes through the other. That's a reasonable thought, but it doesn't work. Because when the photon arrives at the screen, it arrives whole. It's always a whole photon. It's never half a photon. No detector has ever registered half a photon arriving. The photon is indivisible. And yet it seems to have traveled through both slits. And here is where the experiment gets truly strange. Because physicists, being the curious people they are, decided to resolve this mystery by watching. They placed detectors at the slits to observe which slit each photon actually passed through. Surely, they thought, this would settle the question. Did the photon go left? Did it go right? Just look and find out. They looked, and when they did, the interference pattern disappeared. When the detectors were turned on, when it was possible to know which slit each photon went through one slit and one slit only. And the pattern on the screen was exactly what you'd expect from particles. Two clusters, one behind each slit. No interference, no wave behavior, just particles being particles. Turn the detectors off and the interference pattern came back. Turn them on again and it vanished, every time, without exception. And the subtlety of this effect goes even deeper than you might expect. It's not about the physical disturbance caused by the detector. Physicists have designed experiments where the detection process is as gentle as possible, using indirect methods that don't physically touch or disturb the photon in any obvious way. The result is the same. Whenever it is possible, even in principle, to determine which slit the photon passed through, the interference pattern disappears. The key word is possible. You don't even have to actually check the data. If the information exists somewhere, if some physical record of the photon's path has been created, even if that record is sitting in a computer file that nobody will ever open, the interference pattern is gone. The mere existence of which path information, the potential for knowledge, is enough to destroy the quantum interference. There's even an experiment called the quantum eraser that makes this even stranger. In a quantum eraser experiment, you set up detectors that record which slit each photon goes through, which destroys the interference pattern as expected. But then you erase the which path information before anyone can read it. And when you erase the information, the interference pattern comes back. The pattern depends not on whether anyone actually knows which slit the photon went through, but on whether that information is available in the physical world. Erase the information, and the quantum behavior returns, as if the photon somehow knows that its path can no longer be traced. This is the point at which many people start to feel genuinely uneasy, because the experiment seems to be telling us that information itself, abstract, intangible information, plays a physical role in determining what happens. And this unease has been productive because it's driven physicists to think very carefully about the relationship between information and reality, a line of inquiry that continues to produce insights today. Now here's why this experiment has driven physicists to the edge of sanity for over a century. The experiment itself is clean.
The results are unambiguous. There's nothing controversial about the data. What's controversial is what the data means. Because the data seems to be telling us something about the relationship between observation and reality that doesn't fit into any comfortable picture of how the world works. And the story doesn't stop with photons. Because in 1924, a French physicist named Louis de Broglie
proposed something that made the mystery even deeper. If light, which everyone had assumed was a wave, could also behave like a particle, then why couldn't matter, which everyone assumed was made of particles, also behave like a wave? De Broglie wrote down a simple equation. The wavelength of any particle equals Planck's constant divided by its momentum. For large objects, like a baseball or a person, this wavelength is so fantastically tiny, so far below the size of any atom, that you'd never notice it. The wave nature of a baseball is, for all practical purposes, zero.
But for something as light as an electron, moving at the speeds electrons move inside atoms, the de Broglie wavelength turns out to be on the order of the size of an atom. Which means the wave nature of electrons is not a footnote. It's the main event. And de Broglie was right. In 1927, Clinton Davison and Lester Germer, working at Bell Labs in New York, fired electrons at a crystal of nickel and observed diffraction patterns. Diffraction is a wave phenomenon. Electrons were behaving as waves. And separately, George Paget Thomson, the son of J.J. Thomson, the man who had discovered the electron as a particle, demonstrated electron diffraction through thin metal foils. The father won the Nobel Prize for discovering the electron as a particle. The son won the Nobel Prize for showing it was a wave. Both were right. So the double-slit experiment isn't just about light, it's about everything. And this experiment has been repeated not just with photons. It's been done with electrons, with neutrons, with atoms, with molecules made of 60 carbon atoms, buckyballs. These soccer ball-shaped molecules that are enormous by quantum standards, each one made of 60 carbon atoms, locked together in a cage of hexagons and pentagons. The experiment with buckyballs was performed in Vienna in 1999 by a team led by Anton Zeilinger, the same physicist who would later share the 2022 Nobel Prize for his work on entanglement. And what Zeilinger's team showed was that even these relatively large molecules, with masses hundreds of times greater than a single atom, produce interference patterns when sent through a double slit, one at a time. Molecules made of 60 atoms, objects that you can weigh and measure, and whose chemical formula you can write on the back of an envelope, and they still behave as waves. Since then, the experiments have been pushed even further. In 2019, another group in Vienna demonstrated interference with molecules containing over 2,000 atoms, with masses exceeding 25,000 atomic mass units. These are the largest objects ever observed in quantum superposition, and the fact that they still show interference is a powerful reminder that quantum mechanics doesn't stop at some arbitrary size threshold. The boundary between the quantum world and the classical world, wherever it is not where most people intuitively think it is. It's much, much further out. And every single time, with every type of particle and every size of molecule, the result is the same. Unobserved, particles behave as if they passed through both slits, producing an interference pattern. Observed, they behave as if they chose one slit or the other. The act of measurement seems to change what happens. So what's going on? What does this experiment actually tell us about reality? And this is where the story gets truly interesting. Because it turns out there isn't one answer, there are five different ways of interpreting what happens in the double-slit experiment. 5 different accounts of what reality is doing when we're not looking, and what changes when we do look. Each account is internally consistent. Each one is compatible with the experimental results. Each one makes the same predictions about what will happen in every future experiment. But they describe 5 completely different universes. The first interpretation was built in the 1920s by the very people who invented quantum mechanics. It says that the act of measurement genuinely changes the physical world.
that before you look, the photon doesn't have a definite position. It exists as a cloud of possibilities, a wave of probability. And when you look, that cloud collapses into a single definite outcome. Reality, according to this view, is created by the act of observation. This is the Copenhagen interpretation. And for the better part of a century, it was the only interpretation most physicists ever learned. It was presented in textbooks not as one possible reading of the mathematics, but as the answer. The established, agreed upon, don't question it understanding of quantum mechanics. Students who asked too many questions about what was really happening were gently or not so gently redirected toward the equations. The philosophy, they were told, would take care of itself. Just learn to calculate. But beneath that confident surface, the cracks were always there. The Copenhagen interpretation asks us to accept that reality doesn't exist until we measure it. But it doesn't tell us what a measurement is. It asks us to accept that the wave function collapses, but it doesn't explain what causes the collapse.
It asks us to accept that the outcome of a measurement is genuinely random. But it doesn't explain where the randomness comes from, given that the Schrödinger equation, the fundamental law of quantum mechanics, is completely deterministic. These aren't minor complaints. These are holes at the very center of the framework, and some of the greatest minds in physics never accepted them. Let's look at how Copenhagen actually works, where it came from, and why, for all its success, it left so many people unsatisfied. To understand the Copenhagen interpretation, you need to understand the people who built it, because the interpretation didn't emerge from abstract philosophy. It emerged from the specific personalities, intellectual commitments, and sometimes the sheer stubbornness of a small group of physicists working in the 1920s, mostly in Copenhagen, mostly under the influence of one man. That man was Niels Bohr.
Bohr was Danish, born in Copenhagen in 1885, into a family of extraordinary intellectual distinction. His father, Christian Bohr, was a professor of physiology at the University of Copenhagen, known for his work on the physics of blood gases. His mother, Ellen Adler, came from a prominent Danish-Jewish banking family. His younger brother Harold became a brilliant mathematician and, in a wonderful aside, represented Denmark in the 1908 Olympic Games as a soccer player, earning a silver medal. The Bohr household was one where ideas were discussed at dinner with the same intensity and seriousness that other families might devote to sports or politics. Niels himself was quiet, careful, and almost painfully thorough in his reasoning. He was the kind of thinker who would turn a problem over and over in his mind for weeks, examining it from every angle, refusing to commit to a position until he'd explored every alternative and found them wanting. When he gave lectures, people sometimes left the room unsure of what he'd actually said, because his sentences were so heavily qualified, so wrapped in caveats and nuance, that the main point could be hard to find. But when you did find it, it was usually profound. Bohr had already made his mark on physics in 1913, when he proposed his model of the hydrogen atom, the one with electrons orbiting the nucleus in specific allowed orbits, jumping between them and emitting photons when they did. The model worked beautifully for hydrogen, predicting the spectrum of light it emitted with stunning accuracy. But it was a strange model, one that grafted quantum rules onto classical physics without fully explaining why those rules existed. It felt like a sketch, an approximation, a placeholder for something deeper. And by the early 1920s, physicists were desperate to find that deeper theory. It arrived in two dramatically different forms, almost simultaneously, from two dramatically different personalities. The first was Werner Heisenberg, a young German physicist, barely 23 years old in the summer of 1925, brilliant, impatient, and physically miserable. Heisenberg was suffering terribly from hay fever that summer, his face so swollen he could barely see. The pollen in Göttingen was unbearable. So he asked his mentor, Max Born, for leave and took a ferry to Helgoland, a tiny, windswept, treeless, rocky island in the North Sea, about 45 miles off the German coast. The island had almost no vegetation and, crucially for Heisenberg, almost no pollen. It was a barren place, all red sandstone cliffs and crashing waves and cold sea wind. And there, alone on this isolated rock in the ocean, working through the nights by candlelight, unable to sleep from the excitement of what he was finding, Heisenberg developed a completely new mathematical framework for describing the behavior of atoms. His approach was radical. He threw out everything you couldn't directly observe. You can't see an electron orbiting a nucleus. You can't watch it trace a path. What you can observe are the frequencies and intensities of the light that atoms emit. So, Heisenberg built a theory entirely out of those observable quantities, arranging them into mathematical tables that, when he manipulated them, produced the right answers. But the mathematics was strange. When Heisenberg multiplied two of his tables together, the result depended on the order of multiplication. A times B did not equal B times A. In ordinary arithmetic, 3 times 5 is the same as 5 times 3. But in Heisenberg's quantum mechanics, the order mattered. He found this so disturbing that he stayed up all night checking his calculations. And at 3 in the morning, when he'd confirmed the result, he walked out to the tip of the island to watch the sun rise over the sea. He knew he'd found something real, even if he wasn't sure what it was. When he brought the work back to Göttingen, disheveled and elated, his mentor, Max Born, looked at the mathematics and immediately recognized something. Heisenberg, who had no formal training in the relevant branch of mathematics, had independently reinvented matrix algebra, a field of pure mathematics dealing with rectangular arrays of numbers that obey specific rules of addition and multiplication. Mathematicians had been studying matrices for decades, but most physicists at the time had never encountered them and had no use for them. And here was Heisenberg, barely out of graduate school, stumbling onto them while trying to describe the behavior of atoms on a treeless island in the North Sea. Born, together with his student Pascual Jordan, a gifted but troubled young mathematician who would later make the catastrophic moral error of joining the Nazi Party, helped formalize Heisenberg's insights into a complete mathematical framework. It worked. It gave correct predictions, and it was almost impossible to visualize. There was no picture of what was happening, no orbits, no trajectories, just arrays of numbers obeying algebraic rules. You fed in the rules, and out came the right answers. Most physicists found it deeply alienating. It felt like the mathematics was telling you something profound about nature, but refusing to draw you a picture. And Heisenberg went further. In 1927, he derived what became known as the uncertainty principle, one of the most famous and most misunderstood results in all of physics. The uncertainty principle says that certain pairs of physical properties are fundamentally linked in a way that prevents you from knowing both of them with perfect precision at the same time. The most famous pair is position and momentum. The more precisely you determine where a particle is, the less precisely you can know how fast it's moving, and vice versa. This isn't a limitation of our measuring instruments. It's not that our tools aren't good enough. It's a fundamental feature of nature, built into the structure of quantum mechanics at the deepest level. A particle that has a perfectly definite position simply does not have a definite momentum. The two concepts are complementary, like the two sides of a coin that you can never see at the same time. The uncertainty principle has consequences that ripple through all of physics. It's the reason atoms are stable, the reason particles can never be perfectly still, the reason even empty space fizzes with a kind of irreducible quantum energy. And it sets a hard limit on what can ever be known about a quantum system, no matter how sophisticated your technology becomes. And then, just months later, an entirely different approach appeared, one that felt like a breath of fresh air after the cold abstraction of matrix mechanics. It came from an Austrian physicist named Erwin Schrödinger, and the contrast with Heisenberg, both in personality and in method, could hardly have been sharper. Schrödinger was older than Heisenberg, in his late 30s, with a complicated personal life and a temperament that leaned toward the sensuous and the visual. Where Heisenberg was austere and abstract, Schrödinger wanted to see things, to picture them, to build a physical intuition. He'd been thinking about de Broglie's idea that particles have wavelengths, and he asked a natural question. If electrons are waves, there should be a wave equation governing them, the way Maxwell's equations govern electromagnetic waves, the way the classical wave equation governs vibrations on a string. What is that equation? He found it during a holiday in the Swiss Alps in late 1925, at a villa in the ski resort of Arosa. He'd gone there with a woman who was not his wife, and the exact identity of this companion has been the subject of much scholarly and less than scholarly speculation ever since. What is known is that Schrödinger came back from that holiday with the most important equation in all of quantum mechanics. An equation that is to the quantum world what Newton's laws are to the classical world. An equation that every physicist learns, that every chemistry student encounters, that governs the behavior of every atom and molecule and photon in the universe. Where Heisenberg had thrown out all attempts at visualization and worked in pure abstraction, Schrödinger built a wave equation, a beautiful, continuous, familiar-looking differential equation that described how a quantum wave, what he called the wave function, evolved through space and time. If Heisenberg's approach felt like cold algebra, Schrödinger's felt like classical physics in a new dress. Physicists could use the tools they already knew, and when Schrödinger solved his equation for the hydrogen atom, he got exactly the same energy levels that Bohr had found, that Heisenberg had found. But now they emerged naturally from the mathematics of wave behavior. The physics community breathed a collective sigh of relief. Schrödinger's approach was something they could picture, something they could work with. But there was a problem lurking inside Schrödinger's beautiful equation. And it was a problem so deep, so fundamental, that it would haunt physics for the next century and remains unresolved to this day. The wave function, this mathematical object at the heart of his equation, what was it? Physically, concretely, in the real world, what was waving? This might seem like a technical question, but it's anything but. The wave function is the central object in quantum mechanics. Everything in the theory revolves around it. The Schrödinger equation tells you how it evolves over time. The probabilities of measurement outcomes are calculated from it. If you know the wave function, you know everything quantum mechanics can tell you about a system. So the question of what the wave function is, whether it's a real physical thing, like an electromagnetic field, or a mathematical tool, like a coordinate system, or something else entirely, is the question that lies at the root of every interpretation we're going to discuss tonight. For a sound wave, air pressure oscillates. For a water wave, the surface of the water moves up and down. For an electromagnetic wave, electric and magnetic fields oscillate. But the quantum wave function, what was it describing? Schrödinger initially hoped it represented something concrete. Maybe the electron was literally smeared out through space, like a cloud of charge. But that interpretation ran into trouble almost immediately. And the person who offered the interpretation that would stick, the one that became the foundation of the Copenhagen view, was Max Born, back in Göttingen. What Born proposed, in a paper published in 1926, was unsettling in a way that's hard to overstate, because it introduced into physics something that had never been there before. Fundamental, irreducible probability. Not probability as a measure of ignorance, the way we use probability when we say there's a 50% chance a coin will come up heads, knowing perfectly well that the coin's trajectory is determined by Newtonian mechanics, and if we had enough information, we could predict the outcome exactly. Born's probability was different. It was probability as a feature of reality itself. He said the wave function doesn't describe anything physical directly. It doesn't tell you where the electron is. It tells you the probability of finding the electron somewhere, if you look. The square of the wave function at any point gives you the probability of detecting the particle at that point. Not the charge density, not the mass distribution, not some physical substance spread through space. Just probability. Before you measure, the wave function gives you a map of possibilities. The electron might be here with 30% probability, there with 50%, over there with 20%. All of those possibilities coexist, encoded in the wave function, evolving smoothly according to Schrödinger's equation. The wave function is deterministic. Given the wave function at one moment, you can calculate exactly what it will be at any future moment. There's no randomness in the equation itself. But then you measure. You look for the electron, and you find it at one specific location. The wave function, which a moment ago described a spread of possibilities, suddenly seems to snap into a single outcome. The probability is now 100% here and 0 everywhere else. The electron is at this spot. Not spread out, not a cloud, right here.
Bohm called this process the collapse of the wave function. And his probabilistic interpretation was so radical that it earned him the Nobel Prize, though not until 1954, nearly 3 decades after he proposed it. Even Schrödinger, whose equation Bohm was interpreting, disliked the probabilistic reading intensely. Schrödinger once said that if he'd known his wave mechanics would be used this way, he would never have gotten involved. And Bohr, along with Heisenberg and their colleagues in Copenhagen, built an entire philosophical framework around Bohr's idea, a framework that went far beyond what Bohm himself had proposed. The Copenhagen Interpretation, as it came to be called, says something remarkably radical. It says that before you measure a quantum system, asking questions like, "Where is the electron?" doesn't have a meaningful answer. The electron doesn't have a definite position before measurement. It's not that we don't know where it is, it's that there is nowhere specific where it is. The question itself is ill-formed, like asking what's north of the North Pole. The concept simply doesn't apply. When you measure the system, the wave function collapses. The cloud of possibilities resolves into a single definite outcome, and which outcome you get is genuinely random. Not random in the sense that we lack information, the way a coin flip is random only because we don't track the exact physics of the toss. Random in a much deeper sense. Even a being with perfect knowledge of the wave function, with perfect knowledge of the measurement apparatus, with perfect knowledge of everything, could not predict which outcome will occur. The best they could do is calculate the probability. The universe, in this view, contains irreducible, fundamental, non-negotiable randomness. This was what Einstein hated. When he said, "God does not play dice with the universe," he wasn't making a theological argument. He was expressing a deep conviction that the apparent randomness of quantum mechanics must be a sign that the theory was incomplete, that there were hidden variables, pieces of information we hadn't found yet, that would restore determinism if we could figure them out. Surely, Einstein believed, particles really do have definite positions even when we're not looking. We just don't have a theory good enough to tell us what those positions are. Bohr disagreed completely. He didn't just think Einstein was wrong about the specifics. He thought Einstein was wrong about the very framework he was using to ask the question. For Bohr, the demand that particles should have definite properties independent of measurement was itself the problem. It was importing classical assumptions into a domain where they didn't belong. Quantum mechanics wasn't an incomplete description of a classical reality. It was a complete description of a quantum reality that simply didn't obey classical rules. And the debate between Einstein and Bohr, conducted through letters, through conversations, through famous thought experiments at the Solvay conferences of 1927 and 1930,
is one of the great intellectual confrontations in the history of science. The Solvay conferences were gatherings of the world's leading physicists, held in Brussels and funded by the Belgian industrialist Ernest Solvay. The 1927 conference, in particular, has become legendary. Nearly every major figure in quantum mechanics was there. There's a photograph from that conference, one of the most famous photographs in the history of science, showing 29 of the greatest physicists of the century, 17 of whom were or would become Nobel laureates, seated and standing in front of a grand building in Brussels. Einstein would arrive at breakfast with a carefully constructed thought experiment, some ingenious arrangement of mirrors and clocks and particles, designed to show that quantum mechanics was incomplete, that you could in principle determine both the position and momentum of a particle simultaneously, violating Heisenberg's uncertainty principle. He would lay out the thought experiment with characteristic precision, and the other physicists at the table would go silent, sensing that something important was happening. Bohr would spend the entire day in agonized concentration, pacing, muttering, drawing diagrams on napkins, sometimes barely speaking to anyone. And by dinner, pale and exhausted but triumphant, he would have found the flaw in Einstein's argument. Every single time. The pattern repeated at the 1930 Solvay conference, where Einstein produced his most ingenious challenge yet, the famous photon box thought experiment, involving a box that could weigh a photon using a clock and a spring scale. Einstein argued that this setup could measure both the energy and the time of emission of a photon with arbitrary precision, violating the energy-time uncertainty relation. Bohr was reportedly devastated by the argument and spent a sleepless night working through it. But by morning he had found the resolution. In a beautiful irony, the key to refuting Einstein's argument turned out to be Einstein's own general theory of relativity. The gravitational redshift of the clock, due to its position in Earth's gravitational field, introduced exactly the uncertainty needed to preserve the uncertainty relation. Einstein was beaten by his own theory. After that, Einstein shifted tactics. He stopped trying to show that quantum mechanics was internally inconsistent. Instead, he argued that it was incomplete, that there must be a deeper theory, one with hidden variables that would restore determinism and locality. This led, in 1935, to the famous EPR paper, which we'll encounter again later in our story. But here's the thing about the Copenhagen interpretation that's easy to miss. It doesn't just say that measurement produces random outcomes. It says something much more profound. It draws a line through reality and says, on one side of the line is the quantum world, described by wave functions and probabilities. On the other side is the classical world, described by definite outcomes and measuring instruments. And the act of measurement is the moment when quantum becomes classical, when possibility becomes actuality. But where, exactly, is that line? This is the measurement problem, and it is, according to many physicists, including Sean Carroll, the most important unsolved problem in all of physics. What counts as a measurement? What counts as an observer? When exactly does the collapse happen? Consider a chain of events. A photon hits a detector. The detector is made of atoms. Each atom is a quantum system. The photon interacts with the atoms in the detector, and those interactions are described by the Schrödinger equation. At what point in this chain does the wave function collapse? When the photon hits the first atom? When the electrical signal reaches the amplifier? When the needle moves on the gauge? When the physicist looks at the gauge? When the physicist tells a colleague what they saw? There's a thought experiment called Wigner's Friend, proposed by the physicist Eugene Wigner, that makes this problem vivid. Imagine Wigner is standing outside a closed laboratory. Inside the lab, his friend performs a quantum measurement and sees a definite result. From the friend's perspective, the wave function has collapsed. But from Wigner's perspective, Outside the lab, the friend and the entire lab are part of a quantum system that should be described by a wave function. And that wave function, from Wigner's perspective, hasn't collapsed yet, because Wigner hasn't opened the door and looked. So has the wave function collapsed, or hasn't it? It depends on who you ask. And that seems deeply problematic for a theory that's supposed to describe objective reality. Does the measuring instrument need to be macroscopic? Does it need to be conscious? Does a camera count? Does a thermometer count? Does a single molecule bouncing off the particle count? The Copenhagen interpretation, for all its power and precision, never clearly answers these questions. It treats measurement as a primitive concept, something that's assumed rather than explained. And this is where many physicists, both at the time and since, have felt a deep unease. Because if your theory requires you to divide the world into quantum systems and measuring devices, but can't tell you where the boundary is, then something important is missing. Bohr himself was comfortable with this ambiguity, even drawn to it. He had a deeply philosophical temperament, influenced by the Danish philosopher Harald Hofting, and he believed that quantum mechanics was revealing something genuinely new about the relationship between human beings and the physical world. He introduced a concept he called complementarity, the idea that certain features of the quantum world, like the wave nature and particle nature of light, are complementary descriptions that cannot both be applied simultaneously. You can set up an experiment that reveals the wave behavior, or you can set up one that reveals the particle behavior, but you cannot set up one that reveals both at the same time. And neither description alone is complete. Both are needed, but they can never be combined into a single, unified picture. This was, for Bohr, not a bug, but a feature. The universe, he believed, was fundamentally resistant to being captured in a single, all-encompassing description. The best we could do was illuminate different aspects of it from different angles, knowing that no single angle would ever show us the whole thing. He even had a coat of arms design that incorporated the yin-yang symbol, with the motto, "Contraria sunt complementa," opposites are complementary. It was a profound philosophical position, and it gave the Copenhagen interpretation a kind of intellectual grandeur that went far beyond the mathematics. But it also made the interpretation slippery, hard to pin down, and resistant to the kind of sharp, testable claims that scientists usually demand. When pressed on specific questions, like what causes collapse, or what happens between measurements, Bohr would often retreat into careful, densely layered language that his interlocutors found difficult to pass. John Bell, the physicist who would later prove that quantum non-locality was real, once complained that he could never figure out exactly what Bohr was saying, and he suspected Bohr couldn't always figure it out either. For decades, the dominant view in physics, textbooks presented it as established fact. Students were taught to apply the rules, use the wave function to calculate probabilities, accept that measurement produces collapse, and not ask too many questions about what was really going on. And this attitude, which came to be summarized by the physicist David Mermin's memorable phrase, "Shut up and calculate," became the prevailing one for decades. Entire generations of physicists were trained this way. You learned the wave function. You learned the Schrödinger equation. You learned the rules for calculating probabilities, and you were taught, explicitly or implicitly, that asking what was really going on between measurements was not a productive use of your time. It was philosophy, not physics, a distraction from the real work. But there was always a splinter in the mind, always a nagging sense that something was being swept under the rug. Schrödinger himself, one of the founders of the theory, tried to illustrate the absurdity of the Copenhagen interpretation with a thought experiment that has become one of the most famous in all of science. In 1935, he imagined a cat sealed inside a box with a vial of poison connected to a quantum device. If a radioactive atom decays, the vial breaks and the cat dies. If the atom doesn't decay, the cat lives. According to quantum mechanics, before anyone opens the box to check, the atom is in a superposition of having decayed and not having decayed.
And if the Copenhagen interpretation is right, if quantum systems really don't have definite states until they're measured, then the cat, which is linked to the quantum system, should also be in a superposition, alive and dead at the same time. Now, it's important to understand the point Schrödinger was making because it's often misrepresented in popular culture. People sometimes present Schrödinger's cat as a cool, mind-blowing feature of quantum mechanics. Wow, the cat is alive and dead at the same time. But that's the opposite of what Schrödinger intended. He didn't propose this thought experiment because he believed cats could be alive and dead simultaneously. He proposed it because he thought the idea was ridiculous, and he wanted to show that the Copenhagen interpretation led to absurd conclusions when pushed to its logical extreme. If quantum mechanics says that electrons don't have definite positions until they're measured, and if there's no principled reason why the same logic shouldn't apply to cats and people and planets, then something has gone wrong. Either the theory is incomplete, or our understanding of what it's telling us is mistaken. The Copenhagen defenders had their responses, of course. They argued that macroscopic objects like cats are different from electrons, that the act of measurement, the interaction with the environment, ensures that cats are always in definite states. But the boundary between quantum and classical was never clearly drawn. How many atoms do you need before a system stops being quantum and starts being classical? 100? 1,000,000? 1,000,000,000,000? The Copenhagen interpretation never gave a clear answer to that question, and many physicists found that silence unsatisfying. But some physicists couldn't shut up. Some of them kept asking, what if the wave function doesn't collapse? What if there's no special role for measurement? What if the Schrödinger equation, that beautiful deterministic wave equation, never stops working? What if it just keeps evolving, smoothly, continuously, without any sudden collapse? What would the world look like then? The answer to that question is one of the most audacious ideas in the history of science. And the person who first worked it out was a young graduate student at Princeton who, when he proposed it, was essentially laughed out of the room by some of the most eminent physicists alive. His name was Hugh Everett, and he thought the universe was much, much bigger than anyone had imagined. Hugh Everett III was not your typical physicist. Born in 1930 in Washington, D.C., he was brilliant, irreverent, and constitutionally disinclined to accept anything on authority. He was the kind of person who, when presented with a widely accepted framework that seemed to have a hole in it, would go straight for the hole rather than politely working around it. And the hole he found in the Copenhagen interpretation was this. The Schrödinger equation is supposed to apply to everything. It's the fundamental law governing quantum systems, and everything, as far as anyone can tell, is a quantum system. Electrons are, atoms are, molecules are. The measuring devices that physicists use to study quantum systems are made of atoms and molecules, so they should be quantum systems too. And the physicists doing the measurements, they're made of atoms and molecules, so they should be quantum systems as well. If the Schrödinger equation applies to everything, then it should apply to the whole process of measurement. The particle, the detector, the physicist, the lab, the planet. All of it, in principle, evolves according to the Schrödinger equation. And the Schrödinger equation is linear and deterministic. It doesn't contain any mechanism for collapse. There's nothing in the equation that says, and now the wave function suddenly jumps into a definite state. The collapse is something Bohr and his colleagues added by hand, from outside the theory, as an extra postulate. It's not derived from the mathematics, it's imposed on it.
Everett, working on his PhD thesis at Princeton in the mid-1950s, under the supervision of John Archibald Wheeler, asked a simple question. What happens if we don't add the collapse? What happens if we just let the Schrödinger equation run, without interruption, without exception, applied to absolutely everything? The answer he found was startling, and it required him to think very carefully about what it means to be an observer inside a quantum system. Let's walk through this very slowly, because it's the heart of the entire many worlds interpretation, and it's worth getting right. Start with the simplest possible quantum system, an electron that has a property called spin, which can be measured along any direction you choose. When you measure the spin along a vertical axis, you always get one of two results, up or down, nothing in between. And before you measure it, the electron can be in a superposition of both. The wave function describes this superposition precisely. It tells you the amplitude, and hence the probability, for each possible outcome. Let's say it's 70% up and 30% down. Now, what happens when you measure the spin? In the Copenhagen Interpretation, when you measure the spin, the wave function collapses. You get either up or down, with probabilities 70 and 30% respectively, and the other possibility simply ceases to exist. The wave function before measurement described two options. After measurement, only one remains. Reality has chosen. But Everett said, let's not add the collapse. Let's just follow the Schrödinger equation and see what happens. When the measuring device interacts with the electron, the device becomes entangled with the electron. That's a technical term in quantum mechanics, and it's crucial. Entanglement means that the quantum state of the electron and the quantum state of the device become linked. You can no longer describe them independently. They're part of one joint quantum state. Before the measurement, the situation was electron in a superposition of up and down and detector in a ready state. After the interaction, the Schrödinger equation predicts that the combined system ends up in a superposition that looks like this. Electron up and detector reads up, plus electron down and detector reads down. Both outcomes are there, present in the wave function, coexisting in the mathematics. And now, here's where Everett made his crucial move. The physicist, the person doing the experiment, is also a physical system, also made of atoms, also described by a wave function. So when the physicist looks at the detector, the physicist becomes entangled with the detector electron system. And now the combined system looks like electron up and detector reads up and physicist sees up, plus electron down and detector reads down and physicist sees down. Both branches are still there. The Schrödinger equation hasn't gotten rid of either one. Both outcomes have occurred in some sense within the mathematics, and in each branch, the physicist has a definite experience. In one branch they see up, in the other they see down. Each version of the physicist has a perfectly consistent experience of having gotten a single definite result. Neither version has any awareness of the other. No collapse happened, no randomness entered the picture. The Schrödinger equation just kept running, smooth and deterministic and linear, and it produced a state in which both outcomes are present. The wave function didn't choose, it didn't need to. It just evolved, the way it always evolves. And the result is a superposition that includes both possibilities, each one correlated with a version of the observer who sees the corresponding result. And this, Everett argued, is why we think the wave function collapses. It doesn't. What happens is that the universe and everything in it, the electron, the detector, the physicist, the room, the planet, splits into two branches. In one branch, the electron is up. In the other, it's down. And you, the observer, split along with it. The version of you in the up branch sees up. The the version of you in the down branch sees down. From the perspective of either version of you, it looks exactly like the wave function collapsed. You got one definite answer. But from the perspective of the full wave function, the perspective of the mathematics itself, both answers happened. The universe didn't choose. The universe branched. This is the many worlds interpretation of quantum mechanics.
And if your first reaction is something along the lines of, "That's completely insane," you're in good company. That was roughly the reaction of most physicists when Everett first proposed it. His thesis advisor, Wheeler, was supportive but cautious. He encouraged Everett to present the idea to Bohr himself, reasoning that the greatest living figure in quantum mechanics would surely engage seriously with a genuinely new approach to the measurement problem. And in 1959, Everett traveled to Copenhagen to do exactly that, carrying with him a shortened version of his thesis and years of pent-up intellectual passion for the idea. The meeting did not go well. By most accounts, it was a disaster of mutual incomprehension. Bohr, by then in his mid-70s, was deeply committed to his complementarity framework and had spent 3 decades defending it against Einstein's challenges.
He wasn't in the mood to entertain a young American graduate student's proposal to throw out the collapse postulate that he, Bohr, had helped establish as the foundation of quantum theory. The conversations were polite but unproductive. Bohr's younger colleagues, including Auger Peterson and Alexander Stern, were openly dismissive. They saw Everett's proposal not as a new interpretation, but as a misunderstanding of the Copenhagen view. The trip lasted several weeks, and Everett later described it as deeply frustrating. He felt that Bohr and his group had not understood what he was proposing and had made no real effort to engage with it on its own terms. The failure of that Copenhagen trip seems to have been a turning point for Everett, not just professionally, but personally. He felt that the physics community had not engaged seriously with his argument, that the objections were more about philosophical taste than about scientific substance.
And he was probably right about that, at least in part. The Copenhagen interpretation was so deeply entrenched, so thoroughly woven into the culture and the textbooks and the pedagogy of physics, that challenging it felt, to many physicists, less like proposing an alternative theory and more like questioning a shared religion. Everett left academia shortly after completing his PhD. He went to work for the Pentagon, doing operations research and defense analysis, applying his mathematical talents to problems of nuclear strategy and game theory during the Cold War. He made good money. He was respected in his new field. But he never published another paper on quantum mechanics. He apparently kept thinking about it privately, discussing it occasionally with colleagues. But the academic physics community had moved on without him, and he seemed to have decided that there was no point fighting for recognition from people who weren't interested in listening. He drank heavily, smoked constantly, and became increasingly reclusive in his later years. He died of a heart attack in 1982 at the age of 51, alone in his home in McLean, Virginia. His daughter Elizabeth, who had struggled with depression throughout her life, later took her own life, leaving a note saying she wished to end up in the same trash can as her father. Because Everett had told the family to throw his ashes in the trash, which they did. It's one of the saddest and most poignant stories in the history of physics. A man who arguably had one of the deepest insights anyone has ever had about the nature of reality, who saw something that the greatest minds of his generation refused to see, and who was essentially ignored and then forgotten by the community he was trying to contribute to. He didn't live to see his idea taken seriously. He didn't live to see it become one of the leading interpretations of quantum mechanics. He didn't live to see Sean Carroll write a best-selling book, arguing that his interpretation was probably correct. But the idea that Everett set loose into the world didn't die with him. Ideas, unlike people, can survive neglect. The many worlds interpretation was revived in the 1970s by a physicist named Bryce DeWitt, who was working on quantum gravity at the University of North Carolina. DeWitt gave the interpretation the catchy name many worlds, which Everett himself had never used, preferring the more technically precise but less memorable term relative state formulation. DeWitt championed the idea in papers and talks, gave it visibility, and attracted attention from a small but growing group of physicists who felt that the Copenhagen Interpretation's refusal to explain measurement was a genuine flaw, not a feature. The revival was slow. For decades, many worlds remained a minority position, respected by a few and ignored or ridiculed by many.
But gradually, as a new generation of physicists came of age, unburdened by the personal authority of Bohr and the cultural weight of the Copenhagen tradition, the interpretation gained ground. By the 1990s and 2000s, it had become one of the major interpretations of quantum mechanics, with serious proponents including the physicist David Deutsch, the philosopher David Wallace, and, most prominently for a popular audience, Sean Carroll. Carroll, a theoretical physicist at Johns Hopkins and the author of the book Something Deeply Hidden, which is one of the most lucid and passionate defenses of many worlds written for a general audience, has argued forcefully that many worlds is the most natural, most parsimonious interpretation of quantum mechanics. In his book, Carroll makes the case that the measurement problem, the thing that makes quantum mechanics so confusing, is entirely a problem of our own making. We created it by adding the collapse postulate to a theory that doesn't need it. If you just take the Schrödinger equation at face value, if you let it run without interruption, if you apply it to measuring devices and observers and everything else in the universe, you get many worlds. The branching is a consequence, not an assumption. And the measurement problem simply doesn't arise because there's no collapse to explain. His argument is essentially this: the Schrödinger equation works. It's been tested to extraordinary precision. It's deterministic, it's elegant, and it doesn't need any extra postulates about collapse or measurement or observers. If you just take the equation at face value and follow what it says, you get many worlds. No additions required. The branching is a prediction of the theory, not something bolted on. Now, let me be careful here, because the popular image of many worlds is often wildly inaccurate, and I want to be precise about what the theory actually claims. When I say the universe splits, I don't mean there's some cosmic event, some explosion or rupture that creates new universes. The branching is a consequence of quantum entanglement and a process called decoherence, which we'll talk about more later. What happens is that the different outcomes of a quantum event become entangled with their environments, and once that happens, those different branches of the wave function can no longer interact with each other. They're like two radio stations broadcasting on different frequencies. Both signals are there, in the same room, in the same space, but your radio can only tune into one of them. The other is invisible, inaudible, completely inaccessible. The different branches of the wave function are like that. They coexist in the same mathematical structure, but they can't see each other, can't affect each other, can't communicate. Think about the sheer scale of this idea. Every quantum event, every measurement, every interaction that could have gone one way or another produces new branches. And quantum events are happening constantly, everywhere, in every atom of every object. A radioactive nucleus in a rock either decays in the next millisecond or it doesn't. In many worlds, it does both, and the universe branches. A photon from the sun either gets absorbed by a particular molecule in a leaf or passes through. In many worlds, it does both, and the universe branches. An electron in your brain either fires a particular neural signal or doesn't. In many worlds, it does both. And the branching isn't something that happens once in a while during carefully designed laboratory experiments. It's happening constantly, everywhere, all the time.
Every time a quantum event occurs, and quantum events are happening continuously in every atom of every molecule of every object in the universe, the wave function branches. The number of branches is not just large, it's incomprehensibly, staggeringly, almost meaninglessly large. And in each branch, a complete version of the universe exists, with its own stars and planets and people and conversations and cups of coffee and everything else. Now I can hear the objection forming. This seems wildly extravagant. All these extra universes? Isn't that a violation of Occam's razor, the principle that you shouldn't multiply entities beyond necessity? And this is where the many worlds proponents make a subtle but powerful argument. They say, we're not adding anything. The extra branches are already in the mathematics. They're predictions of the Schrödinger equation, which we already believe in and use every day. What the Copenhagen interpretation does is add something, namely the collapse postulate, an extra rule that says these branches get pruned away. Copenhagen adds entities, the collapse mechanism, the mysterious role of measurement, the undefined boundary between quantum and classical. Many worlds takes them away. In this view, many worlds is actually the simpler theory. It has fewer assumptions, fewer postulates, fewer ad hoc rules. It just happens to predict more physical reality. And there's an important distinction between the complexity of a theory's assumptions and the complexity of its predictions. A simple rule can produce complex outcomes. Newton's law of gravity is a single, simple equation, but it predicts the motions of every planet, moon, asteroid and comet in the solar system, an enormously complex set of phenomena arising from a single, elegant law. Many worlds proponents argue that their interpretation has the same structure.
A single, simple law, the Schrödinger equation applied universally, producing an enormously complex consequence, the branching of the universe. That argument is elegant, and many physicists find it compelling, but many others do not. And the objections are serious. The most immediate objection is about probability. In the Copenhagen interpretation, the wave function gives you probabilities for different outcomes. You measure the electron's spin, and there's a 70% chance it's up and a 30% chance it's down. That makes sense. But in many worlds, both outcomes happen with certainty. The universe always branches, so in what sense is one outcome more probable than the other? If both happen, what does 70% mean? This is called the probability problem, and it's one of the most fiercely debated questions in the philosophy of physics.
If you're in a room about to measure an electron's spin, and the wave function gives 70% amplitude to up and 30% to down, Copenhagen says you have a 70% chance of seeing up. That's clear and straightforward. But in many worlds, both outcomes happen. You will see up in one branch and down in another. Both branches are equally real. So what does 70% mean? You can't say you have a 70% chance of ending up in the up branch because there's a version of you in both branches. Both versions are equally real, equally conscious, equally you. The debate has been the subject of intense philosophical work for decades. Various proposals have been made, some involving a concept called self-locating uncertainty. The idea that even though all branches exist, you don't know which branch you're going to find yourself in. And the Born rule probabilities tell you the odds of experiencing each branch.
Carroll and Wallace have developed sophisticated arguments for why this works, using principles from decision theory. But not everyone is convinced. The probability problem remains one of the most serious challenges to the many worlds interpretation. The other common objection is simply aesthetic. It seems, to many people, outrageous. All these universes? Really? And there's a version of me in another branch who decided not to listen to this tonight? And another version who is listening but fell asleep 5 minutes ago? The proliferation of branches feels to some physicists and philosophers less like parsimony and more like ontological excess on a cosmic scale. But here's the thing that keeps many worlds in the game, the thing that gives it staying power even among skeptics. It takes the mathematics of quantum mechanics more seriously than any other interpretation. It asks, what if the equations mean exactly what they say?
What if there's no hidden mechanism? No collapse? No special role for observers? What if the Schrödinger equation is the whole story? And the answer is, then the universe is much, much bigger than we thought. So that's one way of understanding what happens in the double-slit experiment. The photon doesn't choose one slit or the other. It goes through both. Both branches of the wave function are real. And when you detect the photon, you become entangled with it, and the branch where it went left and the branch where it went right separate and can no longer interfere. When you don't detect which slit it went through, the branches haven't fully separated yet, and they can still interfere with each other, producing the pattern on the screen. In many worlds, the interference pattern doesn't disappear because observation collapses the wave function.
It disappears because observation entangles you with the system, and entanglement causes the branches to decohere, to become invisible to each other. The information about which slit the photon went through gets spread out into the environment, into the detector, into the air molecules, into you, and once that happens, the branches can no longer interfere. It's a completely different explanation for the same experimental result. No collapse, no randomness, no special role for observers. Just the Schrödinger equation, doing what it always does. But many worlds is not the only alternative to Copenhagen. There's another interpretation, much older in origin but largely forgotten for decades, that takes a very different approach. It says, what if particles really do have definite positions? What if they really do go through one slit or the other? What if the randomness is just our ignorance, and underneath it all, everything is completely determined?
This interpretation has a surprising pedigree. It was first proposed by one of the founders of quantum mechanics himself, and then independently reinvented by a physicist who paid a steep personal and professional price for taking an unpopular idea seriously. Louis de Broglie was, improbably, a French prince. Literally. The de Broglie family held the title of Duke, which had been in the family since the time of Louis XIV, and Louis himself was born into a world of aristocratic privilege and high culture. He'd originally studied history and medieval literature at the Sorbonne, earning a degree in the humanities before he turned to physics, partly inspired by fascinating conversations with his older brother Maurice, who was doing experimental work with X-rays in a private laboratory in the family's Parisian townhouse. It's worth pausing on that detail because there's something wonderful about it.
A French prince, trained in medieval literature, educated in the reading rooms of the Sorbonne, decides to switch to physics because his brother's X-ray experiments are more interesting than 12th century manuscripts. And within a few years, this literary aristocrat would make one of the most consequential proposals in the history of science. And in 1924, in his doctoral thesis, de Broglie had proposed one of the most audacious ideas in the history of physics. If light, which everyone thought was a wave, also behaved like a particle, then shouldn't matter, which everyone thought was made of particles, also behave like a wave. He even wrote down a formula. The wavelength of any particle, he said, equals Planck's constant divided by the particle's momentum. Simple, beautiful, and experimentally confirmed within 3 years. Electrons do behave like waves. They diffract, they interfere. De Broglie won the Nobel Prize for this in 1929.
But de Broglie also proposed something else, something less well known. something that most physicists ignored or forgot about for decades. He called it the Pilot Wave Theory. Here's the idea. In the standard quantum picture, whether Copenhagen or many worlds, the wave function is all there is. The particle doesn't have a definite position until you measure it. But de Broglie suggested something different. He said, maybe the particle always has a definite position. Maybe it's a real, honest-to-goodness point particle, with a specific location in space at every moment of time. But the particle isn't moving on its own. It's being guided by the wave function. The wave function is a real physical field, spread through space, and it pushes the particle along, like a leaf being carried by a current. In this picture, the wave function still exists. It still obeys the Schrödinger equation. It still evolves deterministically.
But the particle also exists as a point, with a definite trajectory. The wave function tells the particle where to go, and the particle goes. The particle surfs on the wave, so to speak. Hence the name Pilot Wave. De Broglie presented this idea at the 5th Solvay Conference in October 1927. This was the same legendary conference where Bohr and Einstein had their famous debates about the meaning of quantum mechanics, the same gathering captured in that extraordinary photograph showing 29 of the greatest physicists of the century. And at that conference, surrounded by the most brilliant minds in the world, de Broglie stood up and presented his Pilot Wave Theory. The reception was cool, to put it mildly. In fact, it was the beginning of a decades-long exile for the idea. Bohr and his Copenhagen allies were skeptical. Wolfgang Pauli raised technical objections that de Broglie couldn't immediately answer.
And within a year or two, de Broglie himself had abandoned the idea and joined the Copenhagen mainstream. The Pilot Wave Theory lay dormant for a quarter century, and then, in 1952, an American physicist named David Bohm independently reinvented it, in a more complete and mathematically rigorous form, without initially knowing about de Broglie's earlier work. Bohm's version answered the objections that Pauli had raised, and it showed that the pilot wave approach could reproduce all the predictions of standard quantum mechanics. Every single one. Not approximately, exactly. Bohm was a fascinating and somewhat tragic character, one of those figures in the history of physics whose contributions were never fully recognized during his lifetime, partly because of politics, and partly because his ideas were simply too far outside the mainstream.
He'd been a student of Robert Oppenheimer at Berkeley, deeply involved in the theoretical side of physics, and he'd contributed to the Manhattan Project during the war, working on calculations related to the separation of uranium isotopes. His early career was brilliant. Einstein himself reportedly told Bohm that his 1951 textbook on quantum mechanics was the clearest exposition of the subject he had ever read. But in the early 1950s, the political climate in the United States turned toxic for anyone with left-leaning sympathies. Bohm was called before the House Un-American Activities Committee during the McCarthy witch hunts, accused of communist associations. He refused to testify against his colleagues and former fellow students, invoking the Fifth Amendment. He was arrested, indicted, and although eventually acquitted, he lost his position at Princeton. No American university would hire him. He left the country, spent time in Brazil, then Israel, and finally settled in London, where he spent the rest of his career at Birkbeck College. He was an outsider for the rest of his professional life, geographically, politically, and intellectually. And perhaps that distance from the mainstream is precisely what allowed him to see quantum mechanics from a perspective that those inside the establishment couldn't. So how does the pilot wave theory explain the double-slit experiment? Beautifully, actually, and in a way that you can almost picture, which is one of the great virtues of this interpretation. It gives you something to visualize, something to hold on to, in a field that often feels like it's deliberately withholding visual clarity. Let's walk through it carefully. The particle is real. It's a genuine, localized point in space with a definite position at every moment, tracing out a definite trajectory as it moves. When it approaches the barrier with two slits, it goes through one slit and one slit only. There's no ambiguity about this. If you could somehow track the particle without disturbing the wave function, you would see it enter one slit, pass through, and emerge on the other side. Let's say it goes through the left slit, but the wave function goes through both slits. The wave function is a field that permeates all of space, and it passes through both openings, just like a water wave would. On the other side of the barrier, the two parts of the wave function interfere with each other, creating the same interference pattern that waves always produce. And here's the key. The particle's trajectory is guided by the wave function. Where the wave function has a peak, the particle is more likely to end up. Where the wave function is zero, the particle never goes. So even though the particle only went through one slit, its trajectory is influenced by what's happening at the other slit, because the wave function went through both. The pilot wave, reaching through both slits, creates an interference pattern in its own structure, and the particle, following the wave, ends up distributed according to that pattern. If you run the experiment many times, each individual particle goes through one slit, follows a definite trajectory, and lands at a specific point. But the collection of those landing points, accumulated over many runs, builds up into an interference pattern. Because the guiding wave, which each particle is following, has the interference structure built into it. And what happens when you put a detector at one of the slits? The detector interacts with the wave function, disturbing its delicate structure, disrupting the interference between the two parts that pass through the two slits. The wave function is exquisitely sensitive to these interactions. Even a subtle coupling between the wave and the detector can wash out the interference pattern, changing the landscape that the pilot wave presents to the particle. Without the interference structure in the guiding wave, the particles are no longer steered into the telltale bands of the interference pattern. They land in two clusters, one behind each slit, exactly what you observe. And the randomness, the apparent randomness of quantum mechanics, where does it come from in this picture? From ignorance. In the pilot wave theory, if you knew the exact initial position of every particle, you could predict every outcome with certainty. The theory is fully deterministic. But in practice, you don't know the exact initial positions. You can't prepare them with infinite precision. And the distribution of those unknown initial positions, governed by the wave function according to what's called the quantum equilibrium hypothesis, is what produces the statistical predictions of quantum mechanics. Probabilities are epistemic, meaning they reflect our lack of knowledge, not ontological, meaning they reflect genuine randomness in nature. The universe, in the pilot wave picture, has never played dice. It just hasn't shown us all its cards. This is a deeply satisfying feature for anyone who, like Einstein, finds fundamental randomness philosophically distasteful. The pilot wave theory gives you a universe where everything has a cause, where every event follows necessarily from prior conditions, where determinism is restored and randomness is revealed as an artifact of our ignorance. It's the hidden variable theory that Einstein always hoped for, though it achieves this at a cost he might not have been comfortable with. No mystery, no collapse, no branching universes. The particle was always a particle. The wave was always a wave. And the strange behavior of the double-slit experiment is explained by the way the wave guides the particle. Now, this might sound too good to be true, and in some ways it is, because the pilot wave theory comes with its own costs. The biggest cost is non-locality. In the pilot wave theory, the wave function is a real physical field, and it can influence the particle instantaneously across arbitrary distances. When you have two entangled particles separated by a great distance, and you measure one of them, the pilot wave of the other particle changes immediately, everywhere, all at once.
The wave function is fundamentally non-local. Now, to be fair, this kind of non-locality is something that runs through quantum mechanics in general, and the story of how we know that is itself one of the great scientific dramas of the 20th century.
In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a famous paper arguing that quantum mechanics must be incomplete. Their argument, known as the EPR paradox, used entangled particles to show that if quantum mechanics was complete, then measuring one particle could instantaneously affect a distant particle, which seemed to violate special relativity. Einstein called this spooky action at a distance and took it as evidence that particles must have hidden properties, predetermined values that quantum mechanics simply failed to capture. For nearly 30 years, the EPR argument was considered purely philosophical. There seemed to be no way to test whether Einstein was right, whether particles really did carry hidden variables that determined their behavior in advance. But in 1964, a quiet Irish physicist named John Stuart Bell, working at CERN, showed that there was a way to test it.
Bell derived an inequality, a specific mathematical relationship, a ceiling on the strength of correlations, that any theory satisfying two conditions, locality and realism, must obey. Locality means no instantaneous influences between distant objects. Realism means particles have definite properties whether or not anyone measures them. Any theory that has both of these features, any theory that Einstein would have been comfortable with, must satisfy Bell's inequality. And then Bell showed that quantum mechanics predicted violations of this inequality. The correlations between entangled particles, as predicted by quantum mechanics, were stronger than any local realistic theory could produce. If you could set up the right experiment with entangled particles and measure them carefully enough, you could determine whether the universe obeys local hidden variables or whether quantum mechanics is right. The experiments came. In 1982, Alain Aspect in Paris performed a beautifully designed test with entangled photons, closing several loopholes that had plagued earlier attempts. The result? Bell's inequality was violated. The correlations between the entangled photons were exactly what quantum mechanics predicted, and they were stronger than any local hidden variable theory could produce. Nature, it seemed, was non-local. Over the following decades, the experiments got better, more precise, closing more and more loopholes. In 2015, 3 separate groups in Delft, Vienna, and Boulder performed loophole-free Bell tests that closed all the known experimental gaps simultaneously. The results were decisive. Bell's inequality was violated.
And in 2022, the Nobel Prize in Physics was awarded jointly to Alain Aspect, John Clauser, and Anton Zeilinger for their experimental work establishing that quantum entanglement is real and that local hidden variables cannot explain the quantum world. So the non-locality that appears so vividly in the Pilot Wave Theory is not unique to it. All of quantum mechanics is non-local, in the sense that entangled particles exhibit correlations that cannot be explained by any theory where information travels at the speed of light or slower. Bell proved this theoretically. Aspect, Clauser, and Zeilinger proved it experimentally, and the Nobel Committee recognized this as one of the most important discoveries of the 20th century. But in the Pilot Wave Theory, this non-locality is especially transparent. You can see it directly in the equations. The wave function that guides the particle depends on the positions of all the particles in the universe simultaneously.
When you measure an entangled particle on one side of the galaxy, the pilot wave of its partner on the other side of the galaxy changes instantly. The guidance equation is explicitly, unavoidably, non-local. For some physicists, this is a virtue. Non-locality is a real feature of quantum mechanics, confirmed by experiment, and the Pilot Wave Theory has the honesty to put it front and center, rather than hiding it in the formalism. For others, the explicit non-locality is a liability, because it makes the theory harder to reconcile with special relativity, which treats all reference frames as equivalent and doesn't allow for instantaneous influences at a distance. Bohm and his followers have argued that this non-locality doesn't actually allow faster-than-light signaling, so it doesn't violate relativity in any operationally meaningful sense. You can't use quantum entanglement to send a message, but the underlying reality in the pilot wave picture is non-local.
And for some physicists, that's a deal breaker. There's another cost too. In the standard quantum theory, all particles of the same type are identical. Every electron in the universe is exactly the same as every other electron. There's a deep mathematical reason for this, related to the symmetry properties of the wave function. The Pilot wave theory preserves this in the wave function, but it adds the particle positions as extra information. And those positions are not the same for different particles. So in a sense, the Pilot wave theory distinguishes particles that standard quantum mechanics says are indistinguishable. Whether this is a feature or a bug depends on your perspective. Despite these costs, the Pilot wave theory has never been refuted. It makes exactly the same predictions as standard quantum mechanics for every experiment that has ever been performed. It's deterministic. It gives particles definite positions. It explains the double-slit experiment without invoking collapse or branching, and it provides a clear, intuitive picture of what's going on. So why isn't the Pilot wave theory more popular? Why isn't it in every textbook alongside Copenhagen and many worlds? The honest answer is partly sociological, and this part of the story is worth telling because it reveals something important about how science actually works, as opposed to how we'd like it to work. When Bohm published his theory in 1952, the Copenhagen Interpretation had been the dominant view for 25 years. An entire generation of physicists had been trained in it. Textbooks were written around it. Career incentives pointed in its direction. Bohm was already politically marginalized, and his Pilot wave theory was seen by many as an unnecessary complication, a solution to a problem that most physicists didn't think was a problem.
But there's also a deeper reason for resistance. Many physicists feel that the Pilot wave theory, for all its virtues, doesn't really explain quantum mechanics. It explains it away. It takes the weirdness and hides it inside the wave function, which in the Pilot wave theory is just as weird and non-local as in any other interpretation. The wave function is still out there, still going through both slits, still entangling everything with everything. The particle trajectories add a layer of classical-looking behavior on top of it, but the quantum strangeness hasn't gone away. It's just been moved. Whether that's a fair criticism or not is itself a matter of debate. De Broglie-Bohm theory has its passionate defenders and its persistent critics, and it remains, decades after Bohm's lonely reinvention, a serious contender among interpretations of quantum mechanics. Let's step back from the debate between Copenhagen, many worlds, and Pilot waves and approach the measurement problem from a completely different angle. Because there are physicists who find all three of those approaches unsatisfying for different reasons. Copenhagen, because it invokes collapse without explaining it. Many worlds, because it demands an infinity of unobservable universes. Pilot waves, because they require non-local hidden variables that feel to some like an unnecessary addition to the theory. What if there's a simpler way? Let's start with the spontaneous collapse idea, because it's elegant in a way that cuts right through the heart of the problem. In the 1980s, three physicists, Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber, all working in Italy, proposed a modification of quantum mechanics that they called the GRW theory, using their initials. The idea was beautifully simple. What if wave functions don't need an observer to collapse?
What if every particle, all by itself, has a tiny, tiny probability of spontaneously collapsing, of its wave function suddenly snapping to a definite position at any given moment? How tiny? Extraordinarily tiny. almost unimaginably rare for any individual particle. Girardi, Rimini, and Weber proposed that any given particle undergoes a spontaneous collapse, a sudden, random localization of its wave function, roughly once every 100 million years. That's a staggeringly low rate. To give you a sense of scale, the universe itself is only about 13.8 billion years old, which is roughly 138 times that interval. So even in the entire lifetime of the universe, a single isolated particle would only experience a spontaneous collapse about 138 times. For all practical purposes, at the level of individual particles, quantum mechanics works exactly the way it always has. The superpositions persist. The interference patterns form.
The wave function evolves smoothly according to the Schrödinger equation, with these incredibly rare, spontaneous localizations as tiny, almost invisible perturbations. You could watch a single electron for the entire age of the universe and maybe catch a handful of collapses. But here's the crucial insight. A macroscopic object, like a measuring device or a cat or a human brain, is made of an enormous number of particles. A typical visible object contains something on the order of 10 to the 23rd particles. That's a 1 followed by 23 zeros. And if each of those particles has a tiny chance of collapsing at any given moment, the chances that at least one of them collapses at any given moment is essentially 100%. It would happen in a tiny fraction of a second.
And because of entanglement, because the particles in a macroscopic object are all connected and correlated with each other through chemical bonds and electromagnetic interactions and shared quantum states, when one particle's wave function spontaneously localizes, the effect cascades. It drags the entangled particles along with it, like a single thread being pulled in a vast tapestry, tightening everything nearby. The whole object snaps into a definite state, not because anyone measured it, not because of some mysterious observer effect, just because, with enough particles, spontaneous collapse is statistically inevitable. Think about what this means. For a single electron in a double-slit experiment, the probability of spontaneous collapse during the brief time it takes to fly from the source to the screen is negligible. So it behaves quantumly. It goes through both slits, interferes with itself, and produces the interference pattern.
But for a macroscopic measuring device, with its trillions upon trillions of particles, spontaneous collapse happens almost instantly. The device ends up in a definite state, showing one reading or another, not because someone looked at it, but because the sheer number of particles guarantees that the wave function collapses on its own. Think about what this means for Schrödinger's cat. Under GRW, when the radioactive atom is left alone, it can be in a superposition of decayed and not decayed, because it's a single quantum system and spontaneous collapses are incredibly rare. But the cat is made of trillions upon trillions of particles. The moment the quantum event couples to the mechanism in the box, that mechanism couples to the cat, and suddenly you have a macroscopic superposition involving an enormous number of particles. And within a tiny fraction of a second, one of those particles spontaneously collapses, dragging the rest with it, and the cat is either alive or dead. Definitively. Not because anyone opened the box, not because consciousness was involved, just because the mathematics of spontaneous localization applied to a system with that many particles ensures a nearly instantaneous resolution. The cat was never alive and dead at the same time. Or rather, if it was for so brief a moment that no experiment could ever detect it. The GRW theory gives you a clean dividing line between the quantum and classical worlds, and it derives that line from the physics rather than imposing it by hand. Small systems with few particles behave quantumly because spontaneous collapses are so rare. Large systems with many particles behave classically because spontaneous collapses are so frequent. and there's no need to invoke observers, consciousness, or any other special role for measurement. The collapse is a physical process, built into the dynamics of the theory. The cost, of course, is that GRW is not standard quantum mechanics. It's a modification, a change to the Schrödinger equation, and any change to such a spectacularly successful equation had better be made very carefully. The spontaneous collapse, as Girardi, Rimini and Weber defined it, does introduce a tiny amount of energy into the system each time it happens. This means that GRW makes predictions that are very slightly different from standard quantum mechanics. In principle, you could test whether GRW is right or wrong by looking for those tiny energy violations. In practice, the differences are so small that no experiment has yet been sensitive enough to detect them. But this is a genuinely exciting area of current research. Groups around the world are building increasingly sensitive experiments specifically designed to look for these signatures.
One approach involves placing very cold, very heavy objects, things like tiny mirrors or small crystalline beads, into quantum superpositions and watching to see if they collapse faster than decoherence alone would predict. If spontaneous collapse is real, these objects should localize more quickly than standard quantum mechanics predicts. The experiments are fiendishly difficult, requiring temperatures close to absolute zero, near-perfect isolation from environmental noise, and measurement precision at the frontier of what current technology can achieve. But they're underway, and in the next decade or two, we might actually have data that can test GRW and related theories. This is what makes GRW special among interpretations. Most interpretations of quantum mechanics are empirically equivalent to standard quantum mechanics by construction. They're designed to give the same predictions. GRW is different. It's a modification of the theory, not just a reinterpretation.
And modifications can be tested, which means GRW is, in principle, falsifiable, one of the highest virtues a scientific theory can have. But experiments are getting better, and some physicists are actively looking for signs of spontaneous collapse, using extremely sensitive detectors and ultra-cold systems. If they found evidence for it, it would be enormous. It would mean the Schrödinger equation isn't exactly right, that there's a new physical process at work, and that the measurement problem has a concrete, testable solution. But for now, the GRW theory remains a hypothesis, a beautiful one, a testable one, but one without experimental confirmation. And then there's QBism, and QBism is something else entirely. QBism, sometimes pronounced QBism, like the art movement, stands for quantum Bayesianism, though its proponents have largely dropped the Bayesian part of the name and now just call it QBism. It was developed primarily by Christopher Fuchs, Rudiger Schack, and Carlton Caves, starting in the early 2000s. And it takes what might be the most radical philosophical position of any interpretation of quantum mechanics. QBism says, quantum mechanics is not about the world, it's about you. More precisely, QBism says that the wave function doesn't describe the physical state of a system. It describes the beliefs of an agent, a person, about what they will experience when they interact with a system. The probabilities in quantum mechanics are not objective features of the world. They're subjective degrees of belief, like the probability you assign to it raining tomorrow based on what you know and how you interpret the forecast. Think about what this means through a simple example. When a weather forecaster says there's a 70% chance of rain tomorrow, they're not describing a property of the clouds.
They're describing the forecaster's degree of belief based on the data they've seen and the models they trust. If another forecaster, with different models and different data, says there's a 60% chance, neither one is wrong, they just have different beliefs. The probability isn't out there in the clouds, it's in the forecaster's head. QBism
says quantum mechanics works the same way. When you write down a wave function for an electron, you're not describing the electron. You're describing your expectations about what will happen when you measure the electron. Different agents, with different prior experiences and different information, might assign different wave functions to the same electron. And that's fine, according to QBism. The wave function is a personal tool, not a public description of reality. When you measure the electron and get a result, the wave function collapses. But this isn't a physical event.
It's an update of your beliefs. The same way your estimate of the probability of rain changes when you look out the window and see clouds. Nothing physical happened to the clouds when you looked at them, but your beliefs changed. And in QBism, that's all wave function collapse is. A belief update. This neatly dissolves the measurement problem. There's no need to explain what physically happens during collapse, because nothing physically happens. There's no need to worry about what the electron is doing when you're not looking, because quantum mechanics isn't about what the electron is doing. It's about what you expect to experience. The question, what is really going on, is, for QBism, not a question that quantum mechanics is equipped to answer. Quantum mechanics is a user's manual for navigating experience. It's not a God's eye description of the universe. Now, this might sound like QBism is giving up, like it's refusing to do the job that physics is supposed to do, namely, tell us about reality. And many physicists react to QBism exactly that way. Sean Carroll, who is a strong proponent of many worlds, has called QBism essentially a declaration that we shouldn't ask what the theory means. Others have been less diplomatic. But the QBists have a thoughtful response to this criticism, one that's worth taking seriously because it touches on deep questions about what science is and what it can tell us. They say, look at the history of physics. Physics has always been about predicting experiences. When Galileo dropped balls from the Tower of Pisa, or more likely rolled them down inclined planes in his laboratory, he was predicting what he would observe. When Newton calculated the orbit of the moon, he was predicting where observers would see the moon. The idea that physics gives us a God's eye view of reality, a description of the world as it is in itself, completely independent of anyone observing it, is a philosophical assumption that we've smuggled into our interpretation of physics without ever justifying it. And quantum mechanics, with all its strangeness, might be nature's way of telling us that this assumption was wrong all along. QBism takes the role of the observer, which in Copenhagen was mysterious and undefined, and makes it central. The observer isn't someone who collapses wave functions. The observer is the person using quantum mechanics. And quantum mechanics is a tool for that person, calibrated by their experiences, updated by their observations, and fundamentally first person. There's something almost Buddhist about this perspective, if you'll forgive the analogy. The idea that the world we experience is shaped by our interaction with it, that the observer is not separate from the observed, that the map is not the territory and was never meant to be. QBism doesn't deny that there's a world out there. It just says that quantum mechanics doesn't describe that world directly. It describes what happens when we interact with it. And what happens when we interact with it is the only thing we can ever know. Whether you find this liberating or infuriating probably depends on what you think physics is for. If you think physics should tell you what the universe is made of, what's really out there, independent of any observer, then QBism will feel like a retreat. If you think physics is about making the best possible predictions about what you'll experience, then QBism is the most honest interpretation on the table. So let's pause here and take stock, because we've covered a lot of ground. We've now walked through 5 different answers to the question, what happens in the double-slit experiment? What is quantum mechanics actually telling us about reality? Copenhagen says, the electron doesn't have a definite position before measurement. When you measure it,
the wave function collapses and reality is determined. The collapse is triggered by the act of measurement, and which outcome you get is genuinely random. Many Worlds says, the electron goes through both slits and both outcomes happen. The universe branches. There's no collapse, no randomness, and no special role for observers. The Schrödinger equation is the whole story, and it applies to everything. Pilot Wave says, the electron always has a definite position and goes through one slit. But it's guided by a wave function that goes through both. And the wave function shapes the particle's trajectory to produce the interference pattern. Everything is deterministic. There are no branching universes and no collapse. GRW says, the wave function is real and does collapse, but not because of measurement. Collapse happens spontaneously, randomly, and the rate depends on the number of particles involved. Small systems stay quantum. Large systems collapse. No observer required. QBism says, the wave function isn't about the electron at all. It's about your expectations. When you measure the electron and get a result, your beliefs update. Quantum mechanics is a tool for navigating experience, not a description of mind-independent reality. 5 interpretations, 5 different realities, same predictions. And that last part, the fact that they all make the same predictions, is what makes this whole situation so extraordinary and so troubling. Because in science, you're supposed to be able to distinguish between competing theories by running experiments. That's the whole point of the scientific method. You make different predictions, you test them, and nature tells you which theory is right.
But here, nature isn't telling us, at least not yet. All 5 interpretations agree on every experiment that has ever been performed. The data can't distinguish between them, and this raises a question that goes beyond physics, a question about the nature of science itself. So here we are. 5 interpretations of quantum mechanics, each one offering a fundamentally different picture of reality, each one consistent with every experiment ever performed, each one making identical predictions about what we will observe the next time we run a test. This is an extraordinary situation, and it's worth pausing to appreciate just how unusual it is in the history of science. Normally, when 2 theories disagree about the nature of reality, you can design an experiment to tell them apart. That's how science progresses. Newton and Einstein made different predictions about the orbit of Mercury, and the observations sided with Einstein.
The steady-state model and the Big Bang model made different predictions about the cosmic microwave background, and the observations sided with the Big Bang. Competing theories get tested and nature picks the winner. But here, nature isn't picking, at least not yet. There's a word in philosophy of science for this situation. When 2 theories make exactly the same predictions about all observable phenomena, they're called empirically equivalent. And there's a long-standing debate about what to do with empirically equivalent theories. Some philosophers say, if 2 theories make the same predictions, they're really the same theory, just described in different words. The differences between them are merely linguistic, not physical. Others say, no, the theories make different claims about what exists, and those claims matter, even if we can't currently test them. The universe either branches or it doesn't. Particles either have definite positions or they don't. These are questions about reality, not about language. This debate has been going on in one form or another for over a century, and quantum mechanics has made it sharper and more urgent than ever. Because the 5 interpretations don't just disagree about words, they disagree about what the universe is made of. In many worlds, there are an uncountable number of branches of reality. In the pilot wave theory, there are particles with definite trajectories. In GRW, there's a new physical process, spontaneous collapse, that doesn't exist in standard quantum mechanics. In QBism, the wave function isn't even a physical thing. These are radically different ontologies, radically different pictures of what exists. And yet, they all predict the same numbers when you do an experiment. Some physicists are comfortable with this situation, even relieved by it. They say, the job of physics is to predict experimental outcomes, full stop.
If all interpretations do that equally well, then the choice between them is a matter of taste, of aesthetics, of philosophical preference. Pick whichever one makes you happy, or pick none at all, and just use the equations. This attitude goes back to the shut up and calculate era that dominated physics from roughly the 1940s through the 1990s. During those decades, asking questions about the meaning of quantum mechanics, about what the wave function really represents, about what happens between measurements, was considered, at best, an eccentric hobby, and at worst, a career-limiting move. Graduate students were advised to stay away from foundations of quantum mechanics if they wanted tenure. Conference talks on interpretations were politely tolerated, but rarely taken seriously. But there's a growing number of physicists who think this attitude is a mistake, and that it has actually held physics back.
Sean Carroll is one of the most vocal proponents of this view. In his book, Something Deeply Hidden, he argues at length that interpretations matter, that the choice between them has real consequences for how we think about other unsolved problems in physics, and that pretending the question doesn't matter is not just philosophically lazy, but scientifically counterproductive. The measurement problem isn't a side issue, Carroll insists. It's the central unsolved problem of modern physics. And progress on quantum gravity, on cosmology, on the emergence of space-time, may well depend on getting it right. Different interpretations suggest different research programs, different mathematical frameworks, different places to look for new physics. If you believe in many worlds, you might approach quantum gravity by asking how branching wave functions give rise to space-time geometry. If you believe in pilot waves, you might look for non-local structures that could help unify quantum mechanics with general relativity. If you believe in GRW, you might design experiments to test for spontaneous collapse at the boundary between quantum and classical. The interpretation you adopt shapes the questions you ask, and the questions you ask determine what you might discover. And there are also reasons to hope that the empirical equivalence might not last forever. Some interpretations, like GRW, make predictions that differ from standard quantum mechanics, even if the differences are currently too small to detect. As experimental technology improves, as detectors become more sensitive, and as physicists learn to control quantum systems with greater precision, it's possible that some of these subtle differences will become measurable.
And if they do, if an experiment can distinguish between, say, the Schrödinger equation with its perfect linearity and the GRW equation with its tiny, rare, spontaneous collapses, then we'll have real evidence pointing toward one interpretation over another. And there are other experimental avenues being explored. Some physicists are investigating whether gravity plays a role in wave function collapse, an idea originally proposed by Roger Penrose. If gravity causes collapse, then placing a sufficiently massive object in a quantum superposition should produce measurable effects that differ from standard quantum mechanics. Experiments along these lines are being planned, and in some cases are already underway, using tiny mirrors, microscopic oscillators, and other objects that sit right at the boundary between the quantum and classical worlds. There are also theoretical developments that might help. Some physicists are working on understanding how quantum mechanics relates to gravity, And different interpretations of quantum mechanics lead to different approaches to this problem. If one interpretation turns out to be much more naturally compatible with a successful theory of quantum gravity, that would be strong, indirect evidence in its favor. But for now, we're in this extraordinary situation. The most successful theory in the history of science, the one that underpins all of modern technology, the one that has been tested to 12 decimal places, does not tell us what kind of universe we live in. It tells us what will happen, with exquisite precision. But it doesn't tell us what is happening, in any definitive sense. And maybe that's okay. Maybe that's more than okay. Maybe it's something to sit with, to appreciate, to even find a certain kind of comfort in. Because here's what I keep coming back to, lying here thinking about all of this.
Every one of these interpretations agrees on one thing. They all agree on what you will experience. They disagree about what's really going on behind the scenes, about whether the moon exists when nobody is looking, about whether the universe branches, about whether particles have hidden trajectories. But they all agree about what happens when you open your eyes, when you make a measurement, when you interact with the world. Your experience in all 5 pictures is the same. The cup of tea on your bedside table is there in all 5 universes. The warmth of your blanket is there in all 5. The sound of these words, the feeling of your body settling into the mattress, the slow deepening of your breath as sleep approaches. All of that is real in every interpretation. Whatever is really going on at the level of electrons and wave functions and quantum fields, the world you experience, the world of warmth and weight and sound and silence, is robust.
It doesn't depend on which interpretation is correct. It's there, solid and present, and yours, regardless. And there's something quietly reassuring about that. The universe might be stranger than we can imagine. It might branch into infinite copies. It might be guided by invisible waves. It might collapse spontaneously every 100 million years per particle. It might be fundamentally about our own expectations rather than about some external reality. But the world you know, the world you live in, the world where you're lying right now, listening to these words, that world is consistent across all interpretations. It's the one thing they all agree on. And maybe that's the deepest lesson. Physics can describe what happens with astonishing precision. It can build technologies that transform civilization. It can predict the behavior of electrons to 12 decimal places. But it can't tell you, at least not yet, what's really out there. And the honest response to that is not frustration.
It's wonder. Because the fact that the universe is this strange, this layered, this resistant to a single simple explanation, that fact is itself extraordinary. It means there's more to discover. It means the story isn't over. It means that somewhere, in a quiet office or a late-night conversation or a thesis that hasn't been written yet, there's an idea that might, one day, distinguish between these 5 pictures. An experiment that might tell us which universe we actually live in. A new piece of the puzzle that nobody has thought of yet. And until that day comes, we live with the mystery. We live with 5 possible realities, each one beautiful, each one consistent, each one open and waiting for the evidence that might close the case. Let's go back to the double-slit experiment one last time, because I want you to see it now through all 5 lenses at once and appreciate how radically different these pictures are and how remarkable it is that they all produce the same result on the screen. Imagine the experiment running right now. A source is emitting photons, one at a time, toward a barrier with 2 slits. Beyond the barrier,
a screen waits to record where each photon lands. The apparatus is simple. The physics is anything but. In Copenhagen, each photon approaches the barrier as a wave function, a cloud of possibilities spread through space. The wave function passes through both slits, interferes with itself on the other side, and when the photon arrives at the screen, the wave function collapses. The photon materializes at a single point, chosen randomly according to the probability distribution encoded in the wave function. Before it hit the screen, the photon wasn't anywhere specific.
It was everywhere the wave function said it could be, all at once. And the question, which slit did it go through, has no answer because the photon didn't go through a slit. The wave function did. In many worlds, the photon's wave function also passes through both slits and interferes with itself. But when the photon reaches the screen, there is no collapse. Instead, the universe branches. In one branch, the photon hits the screen at one location. In another branch, it hits at a different location. In every branch, a version of the experimenter sees a definite result. The interference pattern builds up because, within each branch, the wave function's interference structure is still guiding where the photon can and cannot land. The pattern is a fossil of the wave function structure, preserved in the statistics of the branching. In pilot wave, the photon is a real particle with a definite position, and it goes through one slit.
But its motion is guided by the wave function, which goes through both slits and forms an interference pattern on the other side. The particle surfs on this wave, following a definite trajectory determined by the wave's structure, and it lands at a point that's shaped by the interference. Run the experiment many times, and the collection of particle landing points reproduces the interference pattern, even though each individual particle took a single definite path. In GRW, the photon's wave function evolves according to a slightly modified Schrödinger equation, one that includes a tiny probability of spontaneous collapse at each moment. For a single photon, that probability is negligible, so the wave function behaves almost exactly like standard quantum mechanics. It goes through both slits, interferes, and the photon lands according to the interference pattern. The spontaneous collapse plays almost no role at this scale. It's only when macroscopic objects are involved that the GRW modification makes a difference. And in QBism, the wave function isn't about the photon at all. It's about you. It encodes your expectations about where the photon will land based on everything you know about the experimental setup. When the photon hits the screen and you see where it landed, your expectations update. The interference pattern is the pattern your expectations take when you let the mathematics of quantum mechanics guide them. The photon's real behavior between the source and the screen is not something quantum mechanics addresses. 5 stories, 1 experiment, same pattern on the screen. And the photon, if photons had opinions, wouldn't settle the argument. It would just land on the screen, make its little dot, and leave the interpretation to us. Now there's one more piece of this puzzle that I want to talk about before we start winding down, because it ties together several threads that have been running through everything we've discussed. And it's the concept that many physicists believe is the real key to understanding why the quantum world looks classical to us. Why we don't see cats in 2 places at once. Why the moon doesn't vanish when nobody is looking, regardless of interpretation. Why the world of our experience is stable and definite and concrete, even though the underlying quantum reality, whatever that turns out to be, is anything but. The concept is called decoherence, and it's something that all 5 interpretations accept, even though they interpret its significance differently. Here's the basic idea. When a quantum system is perfectly isolated from its environment, it can maintain superpositions.
An electron can be in a superposition of going through the left slit and going through the right slit, as long as nothing in the environment interacts with it, in a way that records which path it took. But isolation is almost impossible to maintain. In the real world, every system is constantly interacting with its surroundings. Photons bounce off it, air molecules bump into it, thermal radiation passes through it. And each of those interactions creates a tiny entanglement between the system and its environment. And once the system is entangled with enough pieces of the environment, the different branches of the superposition can no longer interfere with each other. The interference pattern, the hallmark of quantum behavior, gets washed out. Not because the wave function has collapsed, but because the information about the superposition has leaked into the environment, spread across billions of molecules and photons and vibrations, and become effectively inaccessible.
It's as if the quantum superposition is still there, in principle, encoded in the correlations between the system and the trillions of environmental particles it's interacted with. But from the perspective of anyone looking at just the system itself, the superposition has vanished. The system looks classical. It has a definite state. It behaves normally. Let me give you a more concrete picture of how this works. Imagine an electron in a superposition of being on the left side of a room and the right side of a room. If the room were perfectly empty, perfectly isolated from everything, that superposition would persist. The electron would be on the left and on the right simultaneously, and the two parts of its wave function would be able to interfere with each other. But the room isn't empty. It's full of air molecules. And those air molecules are constantly bouncing around, and some of them are going to bump into wherever the electron is.
When an air molecule bounces off the electron on the left, it carries away information about the electron's position. That air molecule is now entangled with the electron. And then that air molecule bounces off another air molecule, which bounces off another. And the information about the electron's position gets spread out into trillions of environmental particles, each one carrying a tiny piece of the story. Once that happens, the interference between the electron on the left and the electron on the right is gone. Not because the wave function collapsed, not because anyone measured anything, but because the information about which side has leaked into the environment, and to recover the interference, you'd need to track every single air molecule that interacted with the electron, and every molecule that interacted with those molecules, and so on, in an exponentially expanding web of correlations that is, for all practical purposes, impossible to unravel. The superposition is still there, in principle, encoded in the correlations between the electron and the entire environment. But it's effectively invisible. The electron, considered on its own, behaves classically. It's on the left or on the right. And there's no observable interference between the two options. Decoherence happens unimaginably fast for macroscopic objects. For a dust grain floating in air, a speck barely visible to the naked eye, the decoherence time, the time it takes for quantum superpositions to become effectively invisible, is something like 10 to the minus 31 seconds. That's a decimal point followed by 30 zeros and then a 1. A trillionth of a trillionth of a trillionth of a second. To give you a sense of how small that is, if you started a stopwatch at the Big Bang and let it run for the entire 14 billion year history of the universe, the number of seconds that would have elapsed is roughly 10 to the 17th.
10 to the minus 31 is 14 orders of magnitude smaller than a single second, compared to the entire age of the cosmos. That's how fast decoherence works for a dust grain. For anything you can see with your eyes, a coin, a cat, a human being, quantum superpositions don't last long enough to be observed. They're destroyed, or hidden, or dissolved by the relentless, omnipresent interaction with the environment almost the instant they form. This is why the world looks classical to us. Not because quantum mechanics stops working at macroscopic scales. It doesn't. The Schrödinger equation applies to cats and people and planets just as much as it applies to electrons. But the superpositions that the Schrödinger equation produces in macroscopic systems are destroyed, or rather, hidden, by decoherence so quickly that we never have a chance to observe them. The classical world, the world of definite objects in definite places, emerges from the quantum world through decoherence.
And here's what's fascinating. All 5 interpretations agree that decoherence happens. They all accept the physics of it. Where they disagree is about what decoherence means. In the Copenhagen Interpretation, decoherence is a welcome ally. It explains why macroscopic superpositions don't persist, why we don't see cats in 2 places at once, why the measuring devices in our labs always end up in definite states. Decoherence provides a natural and physically transparent mechanism for the transition from quantum to classical, and it does so without invoking consciousness or any other mysterious agent. The environment itself performs the measurement, if you want to call it that, by constantly interacting with every quantum system and spreading the information about its state across an exponentially expanding web of correlations.
In this view, decoherence doesn't solve the measurement problem entirely, because the question of why we experience one outcome rather than all of them remains. But it goes a long way toward explaining why the classical world looks the way it does. In many worlds, decoherence is what causes the branches to separate. When a quantum system decoheres, it means the different branches of the wave function have become entangled with the environment in incompatible ways, and they can no longer interfere with each other. The branches are still there, still part of the universal wave function, but they've become effectively invisible to each other. Decoherence is, in the many worlds view, the mechanism by which the universe branches. In Pilot Wave Theory, decoherence explains why the interference pattern goes away when you observe which slit the particle went through. The observation entangles the system with the environment, which changes the shape of the pilot wave, which changes the particle trajectories. In GRW, decoherence and spontaneous collapse work together to produce classicality. Even without decoherence, GRW would eventually collapse macroscopic superpositions. But decoherence happens faster, and it helps explain why the transition from quantum to classical is so sharp. In QBism, decoherence explains why our expectations about macroscopic systems are so reliable and so uniform across different observers. The environment is constantly providing information, constantly constraining what we can reasonably believe, and for large objects, those constraints are so tight and so universal that all reasonable agents, regardless of their prior beliefs, end up with essentially the same expectations. Your expectation that the chair will be in a definite position when you look at it is not a fact about the chair, according to QBism, but it's a fact about what any reasonable person would expect, given the overwhelming amount of decoherence that has already occurred. In this sense, decoherence explains why quantum mechanics, despite being a theory of personal expectations, produces intersubjective agreement about the macroscopic world. Different observers may assign different wave functions to an electron they've never measured, but they all agree about the chair. Same physics, different interpretations. But the physics itself, the decoherence, is real and measurable and universally accepted. And this is, in some ways, the most important thing I've told you tonight, because it means that the strangeness of quantum mechanics, the superpositions and the entanglement and the probability waves, all of that is there, underneath the surface, underlying everything. But the world you experience is shielded from that strangeness by decoherence. The quantum layer is always running, always evolving, always branching or collapsing or guiding or updating, depending on which interpretation you prefer. But the classical layer, the layer where you live, where your body feels warm and your breath comes slowly and the room is quiet, that layer is stable. Decoherence makes sure of it. This picture of classicality emerging from quantum mechanics through decoherence is one of the most important developments in the foundations of physics in the last 50 years. It was worked out in detail by physicists like H. Dieter Zeh, Wojciech Zurek and others, starting in the 1970s and continuing through the present day. And it answers one of the most pressing questions that the Copenhagen Interpretation left open. Why don't we see quantum weirdness in everyday life? The answer is decoherence. The environment is constantly watching, in a sense, constantly entangling with quantum systems, constantly destroying the delicate superpositions that would otherwise produce quantum behavior at macroscopic scales. You don't need a conscious observer. You don't need a measuring device. You just need an environment which is everywhere, always, inescapable. You are, in a very real sense, living on top of a quantum world. The atoms in your body are quantum systems. The electrons in your neurons are described by wave functions. The photons hitting your retina are individual quanta of energy, each one arriving according to quantum mechanical probabilities. But the decoherence that comes from the constant, relentless interaction of your body with its environment, the trillions of air molecules and photons and thermal fluctuations that you're swimming in right now, all of that keeps the quantum strangeness safely tucked away, hidden beneath the surface. The quantum world is always there. You just can't see it from where you're lying. And that, I think, is a beautiful thought to drift off with. That beneath the warmth of your blanket, beneath the solid feel of the mattress, beneath the comforting weight of your own body, there is a deeper layer of reality that even the greatest minds in the history of physics have not been able to fully understand. A layer where particles are waves and waves are particles, where everything that can happen does happen, or doesn't, or follows an invisible guide, or collapses spontaneously, or exists only as a reflection of someone's beliefs. 5 realities, 1 world, the one you're in right now. Earlier tonight, I asked you some questions. Does reality exist when nobody is watching? Is the universe truly random? When you make a choice, is it the only choice, or do all the others play out somewhere else? And if our best theory of nature can't tell us what's real, what does it mean to understand anything at all?
We've seen tonight that these questions don't have one answer, they have 5. And the fact that physics hasn't been able to narrow it down to one, the fact that the universe is still keeping its deepest secrets, that fact isn't a failure of science. It's a sign of how deep the mystery goes. It's a reminder that the universe is under no obligation to be simple or intuitive or fully knowable by creatures who evolved on a small planet to find food and avoid predators. And yet we've gotten this far. We've built a theory that predicts the behavior of nature to 12 decimal places. We've built devices that exploit quantum mechanics to process information, to image the inside of the human body, to communicate through fiber optic cables that span the oceans. We've gone from Max Planck reluctantly introducing a mathematical trick in 1900 to 5 competing pictures of reality, each one more ambitious and more strange than anything our ancestors could have imagined.
That's something to be proud of, and it's something to find rest in. Because the fact that the questions remain open means the story isn't over. There are still discoveries to be made. There are still surprises waiting. And somewhere, right now, someone is thinking about quantum mechanics, lying awake perhaps, turning over an idea, and maybe, just maybe, getting a little closer to the truth. So as you settle deeper into the night, as your thoughts soften and your breathing slows, carry this with you. The universe is stranger than you knew, stranger than anyone knows. And that strangeness is woven into the fabric of everything, into the atoms of your body, into the photons of starlight, into the quiet hum of the quantum fields that fill every tiny corner of space, including the space where you are right now. You're made of quantum mechanics. Every atom in you is a quantum system. Every chemical bond holding your molecules together is a quantum phenomenon. Every breath you take involves quantum interactions between oxygen molecules and hemoglobin proteins. And right now, the electrons in your brain are doing something that no interpretation of quantum mechanics can fully explain. They're generating the experience of being you, of lying here, of listening, of wondering. That's quantum mechanics at work. In you, right now. And whether the universe is collapsing wave functions or branching into infinite copies, or guiding particles along hidden trajectories, or updating beliefs or spontaneously localizing, the experience you're having right now, the warmth and the quiet and the slow drift towards sleep, that experience is real in every single interpretation. There's one more thing I want to leave you with. In the double-slit experiment, when you don't observe which slit the particle goes through, you get an interference pattern. When you do observe, you get two clusters. And there is something almost metaphorical about that. When you let go of the need to know, when you stop trying to pin things down, the world reveals a richer pattern, a more complex beauty. When you insist on certainty, on knowing exactly where everything is and what it's doing, some of that richness vanishes. I don't want to push that metaphor too far. Physics is not a self-help book. Electrons are not life coaches. But there is something in the quantum world that resonates with the experience of falling asleep. The act of letting go, the release of control, the willingness to exist in a state of not knowing, where your thoughts are soft and loose and overlapping, where the boundary between waking and dreaming becomes fuzzy, where certainty dissolves and possibility takes its place. Maybe sleep itself is a kind of decoherence in reverse, a moment when the tightly constrained, classical, definite world of your waking life softens and opens up, when the interference patterns come back, when the waves overlap. During the day, your brain is constantly measuring, constantly collapsing possibilities into decisions, constantly choosing one path and discarding the others. Left or right, speak or stay silent, coffee or tea. Each choice is a kind of measurement, a reduction of the cloud of possibility into one definite outcome. And by the end of the day, all those measurements, all those collapses, all that relentless determination of one thing after another leaves you tired. And then you sleep. And in sleep, the measurements stop. The decisions pause. The need to pin things down, to know exactly where everything is and what it means, relaxes. Your thoughts drift into superpositions of their own, images and memories and fragments of the day blending together, overlapping, interfering with each other in ways that make no logical sense but feel, in the moment, perfectly natural. Dreams are the closest thing we have to quantum superposition at the scale of human experience. Multiple stories happening at once, multiple versions of you existing simultaneously, the rules of classical logic suspended, replaced by something looser, more fluid, more wave-like. Maybe that's a stretch. Maybe a sleeping person is just a sleeping person, and the quantum world is just the quantum world, and the beauty of each is enough on its own, without forcing them into the same sentence. But I'll say this. Tonight, you've thought about things that most people never think about. You've considered the possibility that reality might not exist until you look at it, that the universe might be infinitely larger than you ever imagined, that everything might be determined, or everything might be random, or the question itself might be meaningless. You've held 5 incompatible pictures of reality in your mind simultaneously, and you haven't needed to choose between them. And that's a good state to fall asleep in, a state of openness, a state of wonder, a state of not knowing that doesn't feel like ignorance, but like possibility. The quantum world is strange, and it is beautiful, and it is real, however you interpret that word. And you are part of it. Every atom, every electron, every photon passing through the room right now. It's all quantum, and it's all here with you tonight. So let the questions drift. Let the interpretations blur at the edges. Let Copenhagen and many worlds and pilot waves and spontaneous collapses and beliefs about beliefs all settle into a comfortable superposition of their own, coexisting peacefully in the back of your mind. None of them observed, none of them collapsed, all of them possible. The universe will still be mysterious in the morning. The photons will still refuse to choose a slit. The physicists will still be arguing. And somewhere, in a lab or a lecture hall or a quiet room late at night, someone will be working on the next piece of the puzzle. But right now, you don't need to solve anything.
You don't need to choose an interpretation. You don't need to understand decoherence or wave function collapse or the ontological status of probability. Right now, you just need to rest. The atoms in your body will keep vibrating. The electrons will keep occupying their quantum orbitals. The electromagnetic forces will keep holding your molecules together. All of that will continue, quietly, reliably, in whatever kind of universe this turns out to be. And the quantum fields, those deep, invisible, ever-present fields that underlie everything, they'll keep humming. The way they've been humming since the universe began. So let that hum carry you. Let it be soft and low and constant, like a note played on a very distant instrument, too faint to hear, too persistent to stop. The quantum world, in all its strangeness and all its beauty, is humming right now. In you, around you, through you. And you don't need to understand it to be part of it. You already are.
Right now, your body is doing extraordinary things without any help from your conscious mind. Your heart is pumping blood through 60,000 miles of blood vessels. Your lungs are exchanging oxygen and carbon dioxide across membranes so thin that gas molecules can slip through them in microseconds. Your immune system is patrolling, checking, cataloging. And all of this, every heartbeat, every breath, every chemical reaction in every cell, is running on quantum mechanics. The chemical bonds that hold your proteins together are quantum mechanical. The way enzymes catalyze reactions, lowering energy barriers so that biochemistry can proceed at body temperature, that involves quantum tunneling, particles crossing barriers they don't have enough energy to climb over by passing through them, thanks to the wave-like nature of matter. Even the way your DNA replicates, the way genetic information is copied and transmitted, involves quantum effects at the molecular level. You are a quantum machine. A warm, breathing, wondering quantum machine, lying in the dark, thinking about the nature of reality, using a brain that is itself a quantum system, generating thoughts through processes that quantum mechanics describes, but that no one fully understands. And the night around you is quantum too. The photons from distant stars, each one a quantum of electromagnetic energy, have traveled across billions of light years to reach the atmosphere above you. Some of those photons were emitted when the universe was young, when the first atoms were forming, when the cosmic microwave background was released into the void. They've been traveling ever since, quantum mechanical objects obeying the Schrödinger equation, wave functions spreading through the vastness of space, until they arrive here, on this small planet, in this quiet night, and are absorbed by the atmosphere, or the ground, or the roof above your head. The quantum world reaches from the smallest electron to the oldest light in the universe, and you, lying here between them, are part of all of it. So let your breathing slow. Let your thoughts soften. Let the 5 interpretations settle into a comfortable blur, like lights seen through fog, each one distinct enough to recognize but too far away to touch. Copenhagen, with its sharp collapses and its refusal to describe what happens between measurements. Many worlds, with its infinite branches and its deterministic elegance and its uncomfortable implications about how many versions of you there might be. Pilot Wave, with its hidden trajectories and its non-local guidance and its quiet insistence that particles are always somewhere, even when nobody is looking. GRW, with its spontaneous collapses, its bridge between quantum and classical, its patient wait for an experiment sensitive enough to test it.
And QBism, with its radical subjectivity, its insistence that quantum mechanics is about you, about your beliefs, about your experience, and nothing more. 5 answers to the deepest question in physics. 5 ways the universe might work. And the extraordinary, humbling, wonderful fact that we cannot yet tell which one is right. The moon is out there tonight, whether anyone is looking or not. Or maybe it isn't. Maybe the question doesn't even make sense until someone looks. Maybe it's out there in all 5 interpretations simultaneously, solid and bright and patient, waiting for the next experiment, the next insight, the next sleepless physicist to narrow the possibilities down. But for now, the moon can wait. The interpretations can wait.
The wave functions can keep evolving. The branches can keep branching. The pilot waves can keep guiding. The spontaneous collapses can keep collapsing. And your beliefs can keep updating in whatever quiet way beliefs update when you're drifting off to sleep. You've traveled a long way tonight. From a flashlight and 2 slits in a piece of cardboard, through the philosophical debates of the greatest minds of the 20th century, to the edge of what physics can tell us about the nature of reality. And you've arrived at a place that most people never reach, a place where 5 different pictures of the universe coexist, each one beautiful, each one strange, each one waiting for the evidence that might one day confirm or deny it. That's a good place to rest, a place of possibility, of openness, of wonder. Not the anxious kind of not knowing, but the peaceful kind.
The kind that comes from understanding that the universe is deeper than anyone has yet been able to fathom, and that the search for understanding is itself one of the most extraordinary things that human beings do. So sleep now. Let the quantum world take care of itself for a while. It's been doing fine without your supervision for 14 billion years. And in the morning, when you open your eyes, the world will be there. Solid and warm and familiar. The coffee will taste the same in all 5 interpretations. The sunlight will come through the window the same way in every branch. And the atoms in your body, ancient and quantum and endlessly vibrating, will still be doing their quiet work, holding you together, keeping you alive, being you. 5 realities, 1 morning, and a universe that is still, after all this time, waiting to be understood. Sleep well. The wave function will still be evolving in the morning.